everyone. My name is Pavel, and I will be your MC for today. So I'm happy to announce our first speaker of the day, who will present a new method to construct folding schemes for Stark proofs. Please give a welcome applause to our speaker, Albert Garreta. Okay, we're gonna start a little later. Hello, everyone. Thank you for joining us today at Devcon. So my name is Pavel, and I will be your MC. Let me introduce our next speaker, who will introduce a new method to construct a folding scheme for Stark proofs. Please welcome Albert Garreta.
Thank you. Thanks, everybody, for being here on this Friday morning. So yeah, I will talk about how to folding in the context of Starks. So let's start with the basics. 1 second. All right. So what is folding? So in folding, we have a relation R, relation of interest, which consists of pairs XW. X is an instance or a statement of a problem, and W is a witness or a solution to the problem. And a folding scheme for this relation R is an interactive protocol between a prover and a verifier, where the prover and the verifier have two instances, X1 and X2, and the prover also has two witnesses, W1, W2, and they are valid witnesses for the instances. And then the prover and the verifier interact, and at the end of this interaction, they output a new instance witness pair, X3W3, with this key property. So this output instance witness pair is valid, so it is in the relation. If it is in the relation, then the original two instance witness pairs are in the relation as well, except with negligible probability. So this is the key property of a folding scheme. So basically what is going on here is that we have two tasks. We have to prove one instance witness pair and another one. And we have applied an interactive argument that reduces these two tasks to a single task. So if this folding step is very cheap, then you are basically gaining work, right? You have to do less work because now you only have to prove one instance witness pair. Okay, so commitments play a crucial role in this type of schemes, at least in the modern ones. And in reality, in practice, all instances include a commitment to the witnesses. So in reality, in practice, we have the instance witness pairs look like this. So the instance is a true instance, xi prime, and then it also includes a commitment to the witness. Okay, so a folding scheme looks like this. We have two instance witness pair where the instance contains a commitment to the witness. You fold, you get a new instance witness pair. Okay, and the commitment most of the time is homomorphic, and this is a crucial point. And homomorphic means that the commitment to the sum of two vectors is the sum of the commitments to the vectors. Okay, so if you've never seen folding, this is everything you need to know to follow this talk. Let's look at how folding looks from 5,000 kilometers away. So as I said, in folding you have two instance witness pair of this form. There's a prover and a verifier. The prover knows the instance and the witnesses. The verifier knows the instances. And now they exchange messages. Doesn't really matter what's going on here for the purposes of this talk. And at the end, the verifier sends a uniformly sampled challenge. And then the prover and verifier output a new instance witness pair. The witness is only known to the prover. And crucially, the new instance and the new witness is a linear combination of the initial two using the last challenge sent by the verifier. So we have these formulas in here, x3 equals x1 plus alpha x2, and so on. And the verifier computes so the verifier needs to get the whole instance, right, at the end of folding. So it's easy for the verifier to get x3 because it knows x1 and x2. But how does the verifier get the commitment to W3? Well, here you can use the homomorphic property of the commitment scheme. The verifier knows the commitments to W1 and W2, and because of the the homomorphic property of the commitment scheme, it can obtain a commitment to W3 without any interaction with the prover, just by performing this linear combination of the commitments. So this is how folding looks from 5,000 kilometers away. Many folding schemes look like this. Okay, let's discuss commitments in folding schemes in more depth. So usually, the commitment scheme is a Pedersen commitment or a KZG commitment. So it's an elliptic curve-based commitment, or some variation of Pedersen and KZG. For example, in Nova, Hypernova, Protostar, Protogalaxy, etc., this is the commitment of choice. And this commitment scheme has some inconveniences. One is that here you are forced to live in large fields, so you need fields of at least 250 bits, because otherwise you don't have, if you want to go lower than 250 bits, there's no secure elliptic curves with pairings if you need them. And committing this type of commitments can be extremely expensive if the vector has large entries. And it is expensive to recurse over. So usually in folding, you do folding, and then you do IVC, and then you have to prove that the folding is done correctly, and so on. So you have to prove statements about elliptic curve operations, which are quite a headache. And yeah, because of this setting, you are kind of bound to using a KCG-based snark to prove a folded instance, right? Because you are using large fields, you have elliptic curve-based commitments, and so on. But maybe you want to use a different proof system, right? So that would be that's an inconvenience. Okay, so yeah, let's say we want to use starks to prove our folded instances, our folded instance witness pairs. So by stark, I loosely mean a snark that uses codes and Merkle tree-based commitments. For example, the Stark protocol from Starkware, Plunkett 213, Bujum, RISC0, and so on. These protocols are configured on small fields, and they are getting smaller and smaller. For example, Goldilocks for Plunkett 2, Baby Bear for Plunkett 3, and M31 for Circle Stark. This is the attractiveness of small fields is that, well, the attractiveness of these fields is that you get smaller arithmetizations due to spatial properties of the primes of these fields. You also get cheaper computations because field elements never get very large. If you invert a 32-bit field element, the inverse has at most 32 bits. But there are some problems in the context of folding. The first problem is that Merkle trees are not homomorphic. So if you want to do folding, you don't have the homomorphic commitment right away. And since we are working on small fields, we cannot rely on elliptic curves here. And also, depending on how you are going to do folding, even if Merkle trees were homomorphic, it might not be worth it in the context of starks, and I will explain why now. So let's look at the cost breakdown of creating stark proofs. And yeah, let's look first at how a Fry-based stark works. So yeah, all these proving systems I mentioned before work as follows. So first, the prover computes the trace, or the circuit values, the values in the wires of the circuit. Then it encodes the trace using an error-correcting code, polynomials. And for this, it interpolates the columns of the trace, and then it evaluates the polynomials on a larger domain using inverse FFTs and FFTs. This is called computing the low-degree extension of the trace. Then the prover commits to this low-degree extension using a Merkle tree. And finally, there's some quotient. The prover takes some quotients and applies Fry, and so on. Okay, what's the cost of all this? What's the cost breakdown of all these steps? I'm citing Elie Ben-Sasson from a talk at SBC this summer. So the trace generation, in the case of Stu, costs 46% of the proof, of the total proof cost. Computing the low-degree extension costs 28%. Merkle trees cost about 13%, and the rest also costs 13%. So, yeah, and if we are in the context of folding, if we are thinking of using folding, it means that somehow we want to use recursion. So we are probably not using Merkle trees full of Kechags or SHA-256 or classic hashes. We are probably using Merkle trees that include some type of algebraic hash, in which case the third step would be much more expensive. Yeah, so here's an important observation. Even if the Merkle trees were homomorphic, you don't want to do the folding with the commitments to the low-degree extension of the trace. Because you would, at each folding step, you would perform this step, and this step, and you would save this part in here. And you would still need to do folding. So in the absolute best case scenario, you would save 13% of the total proof cost at each folding step, which is not a lot. So what we are trying to do here is to just commit to this trace in here. We don't want to commit to the low-degree extension with Merkle trees. We are just going to commit to the trace in the most cheap way possible. Yeah, so this is a key difference with approaches like accumulation without homomorphism or the ARC protocol from these researchers that from papers of this from this year. Okay, so let's recap what we want to do. We want to commit to the trace instead of the low-degree extension. We want the scheme to be compatible with Starks, and this means that we have to work over a small field. We want the folded instance to be provable in a reasonable manner with a Stark. And yeah, so since we want an instance to be provable with a Stark, here we think of instances as being heirs or Plonkish instances. And we look at these as CCSs. A CCS is basically an R1CS constraint, but generalized with more terms. Okay, so here is the general framework of what we could try to do if we want to fold Starks. And afterward, I will talk about actual instantiations. So let's say we have two instance witness pairs, two heirs. The framework is as follows. The prover would commit to the trace, not to the low-degree extension of the trace. So the trace, the witness, with a homomorphic commitment scheme. Okay, so now we have these two instance witness pair. And then somehow we would fold in a way that the folded instance is still in an heir or somewhat similar to an heir. And now say that we want to prove a folded instance. So we have done folding, and now we want to prove the folded instance witness pair. So what would the prover and the verifier do? The prover computes the low-degree extension. So we want to use Starks, right, to prove the folded instance. And for if you are using Starks, you have to encode the witness because you are going to use error-correcting codes. So the prover computes the low-degree extension of the folded witness, W3, and commits to it with a Merkle tree, like as if it was just using the Stark protocol. Then the prover proves that the commitment from the folding scheme to the folded witness is consistent with the Merkle tree commitment of the low-degree extension of the folded witness. And then once this is proved, the prover can just finish the proof that the folded instance witness pair is in the relation with his favorite Stark. Okay, so we have to keep in mind that we'll have to do this step in here when we want to prove a folded instance witness pair. So this will inform how we choose the commitment scheme to not make this part in here too expensive. Okay, so let's instantiate the framework now. We need a commitment scheme that is homomorphic, that is compatible with a Stark field, so it somehow works over small fields. And the candidate here is the ITI commitment scheme, getting inspiration from the Lattice-fold paper from Bing-Yi Chen and Dan Bonnet. And we need a folding scheme that folds pairs of heir or Plonkish instances into roughly heirs and Plonkish instances. And the candidate approach here is, if we look at, as I said, if we look at heir or Plonkish instances as CCSs, so let's say R1CSs, or relaxed R1CSs, then the first thing that comes to mind is NOVA, because NOVA folds relaxed R1CSs into relaxed R1CSs. So this is our candidate, NOVA. However, there's no NOVA type folding scheme that works over lattices. So when it comes to folding over lattices, the only work available right now is Lattice-fold, as far as I know. And Lattice-fold is a hyper-NOVA analog that works over lattices, but there's no NOVA analog over lattices. So one of our main results is designing such a folding scheme. Okay, so a bit on lattices and Lattice-fold. So Lattice-fold and many lattice-based schemes work over so-called cyclotomic rings, cyclotomic rings are basically, they look like field extensions, right? You take a ring of polynomials over a finite field, and quotient it by an ideal generated by a polynomial. However, here, the quotient polynomial may not be reducible. And in this case, this means that if the polynomial is not irreducible, it means that this ring splits as a direct product of several field extensions. If f is irreducible, then here there's just one factor, and you have a Galois extension, the standard field extension. But if f is not irreducible, then you have this direct product. But in any case, these rings are quite nice because they are just direct products of field extensions. So you could, in principle, and we show that you can configure R in a nice way, and at the same time choosing F to be a Stark prime field. So we can choose F to be Goldilocks, Baby Bear, the big Stark prime, and probably M31, though this is work in progress. Yeah, and the ITI commitment scheme works on vectors of length m for elements of R. And the parameters of this commitment scheme are as follows. It's just a matrix sampled uniformly at random from the ring with ring elements. It commits to vectors of length m of ring elements. And the commitment is simply the matrix vector multiplication, A times the vector. So let's discuss the efficiency of this commitment scheme first. So and this is an example configuration we can deal with. We can choose the base field to be the Goldilocks field, which has 64 bits. And we can configure R so that R splits as 8 factors, and each factor is a degree 3 extension of the Goldilocks field. Here there's an important remark on how to work with cyclotomic rings. And this is that because of this isomorphism in here, this is the number theoretic transform. Because of this isomorphism, you can potentially store 8 trace cells in a single ring element. So if you want to store 8 trace elements, and each element is in the field, you can put each element in one of these components, and then these 8 elements become just one ring element. So a vector of size 2 to the n with ring elements can store 2 to the n plus 3 trace cells. And this is quite relevant for performance. And this is some benchmarks of our implementation of the ITI commitment scheme using this configuration. So say we want to commit to a vector of size 2 to the 16 field ring elements, and this means 2 to the 19 field elements. So this costs 65 milliseconds. This should be the commitment time. I don't know why it says field. And this is, for comparison, what you would get if you commit if you do Merkle tree commitments to the vectors. So if you commit to 2 to the 16 field elements with a Blake function, so classic hash, this is 14 milliseconds. But as I said, this is just 2 to the 16 field elements. This is 2 to the 19 field elements. Also, if you are using Merkle trees, you probably have encoded the witness, which means that here you have an extra 1 in the exponent, which is not giving you anything when you want to encode the witness. Maybe the overhead is even larger if the rate of the code is less than 1/2. Yeah, so if we compare 2 to the 19 and 2 to the 19, we get similar performance. And if we put algebraic hashes in the Merkle trees, which we probably have to if we are in the context of folding, because it means we are interested in using some kind of recursion, then the difference of cost is dramatic. How much time do I have? 5 minutes? OK. So yeah, we are almost. There's 1 or 2 slides left. So recall, an ITI commitment is just matrix vector multiplication of ring elements. There's a big issue with this commitment scheme. I said what is good about it, and now what's bad about it. This commitment scheme is only binding when the vector you are committing to has small norm. And the norm of a vector is the largest coefficient of an entry of the vector when you look at the elements of the ring as polynomials. And yeah, remember that the folded witness in our folding schemes are a linear combination of the 2 initial witnesses. So there's 2 issues here because of this caveat. One is that even if W1 and W2 have small norm, because W3 is a random linear combination of W1 and W2, it is possible that W3 has large norm. In general, W3 might have arbitrarily large norm, in which case the commitment to W3 with the iTie commitment would not be binding. And there's another issue that is, even if one does not happen, even if W3 has low norm for some reason, when you prove knowledge soundness of the folding scheme, you need to make sure that the extractor gets witnesses of small norm. Because of this caveat, we only commit to witnesses of small norm, so we end up requiring that the prover commits to witnesses of small norm. So when you prove knowledge soundness, you need to show that the extractor only gets witnesses of small norm, and this is quite difficult to enforce. Okay, so since there's 5 minutes less than I had planned for, I will skip how lattice fold and how we address these two issues and just jump to the Q&A part. Thank you.
Yeah, thank you very much. So we have one question. So why M31 is WIP, and because of the two adicity, or?
Yeah, the thing is that there's a lot of factors coming into play when configuring these rings. We have to configure them in a way that when they split as field extensions, they have at least 128 bits to ensure soundness during sum check. And at the same time, we have to ensure that there's a subset of small norm elements that is large enough for the soundness in another part of the protocol. And this places a lot of constraints on how you can choose the cyclotomic polynomial. Yes, but the composition of P-1 is completely different. The way you can choose the way you can configure the ring is highly constrained on the factorization of P-1, on how it factors.
Do we have any other questions? Okay, if there's no questions, then we're gonna take a 5-minute break. So thank you, Albert, again for a nice research. I really enjoyed the talk. And we're going to continue our session with two lightning talks. So let me introduce our next speaker, who will talk about how zero knowledge and blockchains will help humanity survive. Please welcome Lisa Acklesworth.
Hello, everyone. This is a lightning talk, meaning we don't really have any time for jokes. Sorry for that. We have to start being very serious from the very beginning. So the question I'm going to talk about today, the problem is that we are very small. Like as a blockchain industry, I mean. On this picture, you can see how the rest of the world is trying to see what is blockchain. If you want some more specific numbers, if we compare our industry to other tech verticals like space tech or biotech, we are something like 10 to 40 times smaller. Frankly speaking, we are like a small dot. But I think we need to be large. If we want our industry to prosper and take a meaningful place in the world. And I think we need to learn from mushrooms how to be large. What's the difference between blockchain and mushrooms? Blockchain is a 3-mushroom network. And mushrooms are a 3 trillion mushroom network. 3 trillion mushroom network is a really cool thing. Whenever someone sees it, they want to jump in, because if there are 3 trillion mushrooms who joined, it seems to be worth it. But 3-mushroom network seems to be a bit a doubtful activity. So we need to become mushrooms. That is to say, it is on us as a blockchain industry to find use cases where blockchain and ZK are a perfect fit for huge world's problem. And furthermore, it's on us to communicate it to right people in right industries and in right countries around the world. Because I can guarantee you, they will not figure it out on their own. First, because they don't think about blockchain, then because they don't know about zero knowledge. So today, I'm going to, just as an example, give you 3 real-world use cases that are crucial for humanity's survival. And I'm going to use the formula of ZK for verifiable computations and blockchain for coordination. Think, for example, about the space. Think, for example, about satellite coordination. There are many countries operating in the space, and many of them are not friends, but still they have to coordinate their activity in the space. How can China prove the US that their satellite won't clash into some US space facility? What they do today, they ask, you promise? Yes, I promise. But what if they use zero-knowledge proofs for proof of root or proof of hitting the specific coordinate instead of just promising? But how should they coordinate these tons of zero-knowledge proofs by hundreds of parties for thousands of satellites 24/7 without disclosing any sensitive information? They can use privacy-preserving programmable blockchain. Or think about agriculture. In many countries, agriculture is run by self-piloting machines like computers with software running on it. If tractors, cultivators, and balers are out of operation for the whole country, its economy stops and the country is in deep economic crisis. How can a small human force thousands of machines with different programs running on top to report them what's on their mind? Using zero-knowledge proofs. But what about a network of thousands of machines and thousands of humans transmitting zero-knowledge proofs in arbitrary directions 24/7 with privacy-preserving programmable blockchain? Or think about nuclear missiles. I know this is not the favorite topic for most people, but just for 30 seconds. If a country A has a concern that a country B launched a nuclear missile towards it, its president has several minutes, less than 5, to call their president and ask, did you do it? And if the president didn't answer, they must launch all their missiles as a prevention. But can we prove that something has not happened? Can one prove that they have not launched the nuclear missile? Or if they did, can they prove that this particular country is not a destination? I don't have 100% answer for this one, especially if we can prove that something has not happened, but I think it might be doable, and I think it's worth thinking about it. So Can zero knowledge help humanity survive? Yes, sure. Can blockchain help humanity survive? This is a bit trickier, but yes, but it must be privacy-preserving programmable blockchain. No privacy, no blockchain adoption. That's simple. That's it. Thank you.
Thank you for interesting talk. I also strong believer that blockchains and their proof of knowledge will help humanity to reorganize in the future. And thank you again. So if we have any questions, we have some time. Okay, then let's try to kind of stay together because the next lightning talk will be started in 2 minutes. Thank you.
May I answer the fourth one?
Yeah, if you want.
Yeah, about proving to the partner that someone is not cheating. If you're a computer, I think, and she's a computer, I think it is very easy. If one of you is not the computer, it is tricky because when it comes to bridging data from the physical world into the digital world, from my perspective, this is very still very tricky thing, and it wasn't resolved so far. There was a paper in 2013 written by some Princeton guys about utilizing zero knowledge proofs for monitoring the state of nuclear facility, and they assumed that there is some nice solution to a nice solution for an oracle from physical world to the digital world. But up to now, there is no such solution as far as I know, and that's why all the cases I described, they are digital and native from the very beginning. So something exists like a piece of code from the very beginning, like self-piloting machine or like satellite.
Thank you. Yeah. Okay, we're going to continue with our lightning talks, and next speaker will talk about based rollups and preconfs. So please welcome Jason Vranek.
All right. Thanks for coming, everyone. I know it's kind of early. So this is a lightning talk on based rollups and preconfs. And as you know, these lightning talks are extremely quick. So this isn't going to answer all of the questions. It's really going to try and lay the foundation and motivation for why different teams are working on this. So I would want to start with like, what is the big motivation here? And the big goal of these based rollups really is to help solve this fragmentation issue we're starting to see in the L2 space and to restore some value capture back to the base layer. So how did we get here? Well, Ethereum's always in this tricky position. The goalposts always move. Gas was too expensive. We created this rollup-centric roadmap. We succeeded in offloading all of this execution. Things got cheaper, TPS increased, but ETH is dead. So we really want to try and address some of these problems head on. And the big focus of this talk is around fragmentation. So currently, these L2s aren't interoperable with each other. They fragment liquidity, they fragment users, they also fragment developers. You have to pick a winning ecosystem to deploy on or deploy across many, which starts to spread your resources. And what we're really seeing is this kind of convergence on what I'm calling intra-op. You have interoperability within your ecosystem, but not across these ecosystems. So how do we fix this fragmentation problem? Well, one easy solution is that we just agree on one entity to sequence all of these rollups. And that sounds pretty centralizing. So can we do this in a way that preserves a lot of the values that we care about? So enter based rollups. The idea here, this is a quote from Justin's paper. The TLDR here is, it's a based rollup when it's sequenced by Ethereum validators. So in this picture, on the left-hand side here, we have centralized sequencing. The idea is you have these unordered transactions. A centralized sequencer's job is to order them for the rollup. These little squiggly things are the rollups at the bottom here. Okay. As we move to the right, we're increasing in decentralization and we're unlocking interoperability. So with shared sequencing, you have multiple parties that are all agreeing according to some leader election mechanism on who has the ability to sequence all of the rollups. And as we move all the way to the right, we enter this based sequencing mode. The idea is that the transactions for these L2s will be sequenced directly by Ethereum validators. And how does this help? How does this unlock interoperability? The idea is that we have these write locks over L2 state. When an Ethereum validator is going to propose a block, they have a write lock over the entire L1 block and all of the L2 blocks that are going to be included. And when we have a bunch of rollups that are all agreeing to be sequenced by this validator, it unlocks this ability for you to start passing messages across these rollups. We don't need these bridges. We're able to do these more seamlessly. So this has limitations. One of the big issues with based rollups is that they have really 12-second block times. A lot of users want to come to L2s because they care about that snappy UX, those instant transactions. We can always reduce the L1 block times, but that's a very long, arduous process that has a lot of unknowns and centralization vectors. So preconfs, this is another one of these new terms. It stands for pre-confirmations. A preconf is a commitment made by these validators to users about doing something related to block proposals. So this could mean I'm giving a guarantee to a user that I'll include their transaction when it's my turn to propose the block, or I can even give a stronger guarantee, like this will be the state after executing your transaction. And if I break my promise as the pre-confer, then I can get slashed on various means. So to kind of wrap this up, like how does this all come together? So the user over here would be able to send their rollup transactions to be sequenced by an Ethereum validator. They, in response, give back this pre-confirmation signature, which is like this receipt for the users, guaranteeing that their transaction will be included or it'll be executed inside of the rollup. And if the validator does break this promise, they can be slashed by submitting evidence to the slashing contract. And what does this enable? Well, it solves a lot of these UX problems. And when we start to enter this like execution preconfs, we really make it to a place where we can actually outperform these alt L1s by giving these very instant transactions back to users. And this all comes without modifications to the base layer. So hopefully this maybe piqued people's interest on this topic, but of course in a 5-minute lightning talk, there's still many things to be explored. So thank you all for joining.
Okay, yeah, we have a few questions.
Right, yeah, so the first question here, how does this notion scale if they need to validate all of the L2 transactions? So this is a great question. So I think there's kind of two worlds here. Like one is sequencing itself doesn't imply execution, so it doesn't have to take on all of the load. But realistically, there's different implementations of these preconf protocols being built. Some of them offload this duty to these kind of gateways is what they're called, similar to the PBS pipeline we see today. Second question, pre-confirmation services seem to be the biggest layer of complexity for me. These pre-conf networks will likely require consensus. Is this the biggest drawback? So definitely over the past year, like it started from this like very dark forest unknown, and over time we've started to untangle it. And some of the bigger questions are now just around pricing, but really you don't need an actual consensus protocol to build this. You're able to just broadcast like these messages directly to the users, and if the user like doesn't get their pre-confirmation, they're able to go and slash.
Okay, maybe one last question. Why is Spire better than Puffer?
Why is Spire better than Puffer? Well, we're all here building based rollups, so yeah.
I understand. So everyone has their own vision for the best approach. Thank you very much. So thank you. Please give a round of applause to our speaker. Okay, we're gonna continue with the next lightning talk. So our next speaker will talk about practical approach to unifying Ethereum using next generation based rollups. Please welcome M-Team.
Hello, Devcon. All right, so we're going to talk about next generation base rollups today. There are some base rollups that are next generation. There are some base rollups that are last generation. You guys just learned about some. I'm going to tell you more about how you can become a next generation base rollup, kind of what the definition is, and then a little bit more about how I see the future of base rollups evolving. Cool, so this first section, we're just going to go through some of the traditional base rollup research, talk about the base rollups that have been explored in the past, some of the designs that have been proposed, and then we're going to understand some of their flaws, some of their weaknesses. So one of the very first designs that is used by Tycho today on mainnets is total anarchy base sequencing. This is like kind of letter of the law, exactly what Justin Drake proposed in last year, right? And it's very simple, very basic, right? It's called total anarchy because it uses a election system that is permissionless and allows anyone, that's the anarchy bit, to propose a block. So one key point here is that the sequencer is not elected beforehand. You don't know who the sequencer will be beforehand. You might know the Ethereum proposer because you can look at the Ethereum lookahead. We know 32 in advance. But the sequencer of the base rollup might not be the proposer. Tycho's case, it is Tycho Labs for the majority of blocks. One other thing to note is that layer 2 block proposing is completely permissionless, right? There's no permissions involved. The way that this ends up playing out in practice is that we have this diagram up here. We have a bunch of sequencers, proposers in Tycho's system that give their blocks to the builder, to the Mev-boost builder, that would be Titan, Wintermute, etc. And they would take these blocks, order them in the layer 1 block, so each block proposal is a layer 1 transaction, and then send this completed block to the proposer through a relay and through the Mev-boost auction, right? And then eventually the proposer would propose this to Ethereum once they've selected the block with the highest bid. So it's up to the proposer and the builder to choose which block created by these layer 2 sequencers or proposers actually gets onto the chain. Now, one design that aims to solve a few of the problems of the previous design is vanilla-based sequencing. So LimeChain, George Spasov put out this excellent bit of research that explained how we can actually solve a few of the foundational problems with total anarchy-based sequencing, right, the Tycho model. So the first kind of thing that we try with vanilla-based sequencing is a simple sequencer election, right? That gives us the ability to choose a sequencer based on some rule. We have a primary rule, and then we have a fallback as well. So the fallback in vanilla-based sequencing case is just total anarchy. So there's still some total anarchy here. And the primary sequencing is based on some election mechanism that is not clearly defined and kind of left to implementation in the initial research. So the other thing that vanilla-based sequencing includes is kind of very basic primitive support for delegation, which is allowing the Ethereum proposer to give the rights to their base rollup block to an external builder without directly going through Mev-boost. It's like external to the Mev-boost auction. Vanilla-based sequencing also included basic support for preconfirmations, which gives the, we heard about it last talk, but it gives the proposer the ability to promise things about the block that they will eventually propose. It does require some sort of delegation or some increased hardware constraints on the proposer. And so the design for preconfirmations has kind of wide-reaching implications for centralization vectors, for stake, and also for preconfirmations in real time. Now, the other thing that vanilla-based sequencing introduced that really caught my eye was revenue generation from a % of congestion fees. And you'll hear Justin Drake talk about this all the time. You'll hear me talk about this. Base rollups can capture revenue from congestion trivially, right? These base fees, if you're doing EIP 1559 EVM, right? They are represented on chain and are kind of understandable from within the EVM, within the state transition function. So you can view things about the fees. You can take these and you can do things with them, right? You can direct them to a treasury. You could give some of them to the proposer, or you could return them back to users. So kind of the problems with these that are actually really big problems, like Tycho on mainnet live is extremely inefficient. All forks of Tycho without major changes will continue to be extremely inefficient. One other problem with kind of total anarchy and vanilla-based sequencing is that there's kind of no built-in composability. Any composability is on a layer above the sequencing. And that's really unfortunate because whenever you have to build kind of another layer, you introduce complexity and centralization vectors of some sort. In the case of base rollups, that's quite possibly around pre-confirmations, which means we could have centralized Ethereum stake, which we all want to avoid. The other thing is MEV revenue. So lots of people still have this misconception that base rollups leak MEV revenue, and that's true for traditional base rollups because they do not use an auction of any sort to kind of get an oracle into MEV. So if we look into layer 1 MEV research, we'll see things like execution tickets and execution auctions that are all designed to get some oracle price, essentially, of the MEV in a block. Now, the other thing to note about base rollups, like I mentioned before, is inefficiency. So Tycho has about a $10,000 a day cost to do their sequencing. Before blobs, they had about $100,000 a day. This is a lot of money, clearly, and the kind of thing that you need a massive amount of users and network effects to actually be sustainable, right? And that's something we obviously want to avoid. But there is a solution. For some of these Tycho forks, we've been looking at doing slower block time. So Tycho now has a block time of 33 seconds instead of 12 seconds, which is, of course, Ethereum block time. That has allowed their cost to come down by about a third, which is good for them. But it's also really bad for users. You get a worse user experience. So the way we can patch over this is with pre-confirmations. Just throw some preconfs on top. The downside of that is that without doing your pre-confirmation designs in a clever way, you're going to end up with limited benefits. So your users are going to get very limited availability of pre-confirmations, and of course, limited composability. So unless you're using a shared pre-confirmation protocol, you're not going to have composability. So we start breaking a lot of things when we add pre-confirmations. The other thing that specifically Tycho's case, you lose composability with layer 1 because pre-confirmations happen over a course of an entire epoch perhaps, and during that time layer 1 state could change a ton. And so the kind of current layer 1 proposer is very different than who's actually sequencing the rollup. That's not shared sequencing, that's not based. But we can do better. Traditional designs are not good enough. We have, over the past 2 years, we have new research, we have new teams, we have a lot more data about base rollups because we have one live, and we have a lot better technology. So one of the big things that we'll be talking about in the next section is ZK, using snarks to save costs and improve efficiency. So let's kind of take a step back. Let's think from first principles with all the data, with all the research, and with all the teams that we have now, kind of what are the things that we really want to get out of base sequencing? The first thing is, in my mind, the most important, which is synchronous atomic composability. And this is a buzzword for sure. What I think that means is atomic cross-chain contract calls that are sufficient enough for flash loans. And the reason for that is because flash loans are a foundational tool for doing atomic arbitrage between domains. So once you have cross-chain contract calls, you can do arbitrage. You can do flash loans for arbitrage. And this gives you the ability to essentially arbitrage prices on different domains, giving users kind of the best prices across chains. You can also use that for doing like a swap that uses multiple chains liquidity. If I'm on Arbitrum, I could directly use Ethereum layer 1 liquidity without waiting for like a service provider or some collateral. Now, that's pretty straightforward. The other thing to look at is a seamless user experience and developer experience. So anyone who's ever tried making an asynchronous application will know that it's 10 times easier, I'm not joking, to build a synchronous application. If it's asynchronous, you have to deal with a case where something goes wrong and you have a desync. Now, the other thing is, of course, network effects, right? Once we have the efficient synchronous composability between chains, we have the ability to build network effects on one chain and use that on another. And because Ethereum already has massive network effects, that means base rollups can use those network effects, those liquidity users, protocols, etc., to directly improve the user and developer experience on their rollup. Now, the other thing that we want, of course, all the time is faster things and cheaper things. So on the faster side, we're looking at good pre-confirmations that don't break things and that are fulfilled 100% of the time. Frequent block proposing. The more we touch Ethereum, the more we can compose with Ethereum. Custom front ends. So this is kind of changing the Uniswap style swap interface to something that can actually represents what a pre-confirmation might look like. So that's a green check mark, some confetti of some sort. It doesn't seem like a lot technically, but it's actually really important to improving the user experience materially. One thing is like getting rid of improvals and then swaps. We can get rid of that completely with pre-confirmations. Another thing is, of course, cheaper things, which is better execution. So just writing your smart contracts better and not making kind of the mistakes that we've made in the past when we were rushing to get code out. Aggregate everything. There's a slide on that, so I'll wait. And of course, efficiency of all shapes and sizes. Now, we want to do all of these things, and both of these things, I guess, without sacrificing decentralization and censorship resistance, liveness, and sustainability. So this is where you can get faster and cheaper if you go to all layer 1. You can do it on a centralized sequencer or layer 2. What you can't do is faster and cheaper with decentralization, censorship resistance, liveness, and sustainability without some form of base sequencing is my opinion. So we know what we want. It's not that complicated. We want fast things, we want cheap things, and we want everything to feel like one chain for developers and for users. Getting there. Next generation base sequencing. This is the subject of these 3 companies up here. This is kind of the industry that we're in. This is Rise, Spire Labs, and Tycho Gwyneth. And we're taking a very practical approach to unifying Ethereum. So we're trying to avoid the kind of discussions where we get into the ivory tower semantics and actually build like tangible, useful products that are good for users and developers. So let's get into the specifics. This is a intermediate talk, so we're going to get a little bit technical here. We're going to share literally everything. So when it comes to things we share, like if the answer is no, then you're probably lying. We have deposits, proposing blobs, proving network effects, assets, contract calls, off-chain infra, security, economies of scale, et cetera, et cetera, et cetera. So shared deposits, that's ag layer. These are teams that are working to reduce cost of posting ZK proofs to mainnet by aggregating ZK proofs. Also has the excellent benefit that you can do interop between layer 2s without ever touching layer 1, so you save a lot of costs with that as well. Shared proposing saves a lot of costs and enables atomic composability, again, between base rollups. If we can share blobs, so if you're a base rollup and you're frequently checkpointing or posting to Ethereum, you're going to be purchasing a blob for DA in most cases. And blobs are pretty big, and most base rollups do not use 100% of the blob space in a single blob. So there's a lot of empty space. And there's a whole bunch of teams. Spire is kind of leading some of the research on this side to figure out how we can have multiple rollups use the same blob. So we build some crypto economic system to make everything a little more efficient and a lot cheaper for base rollups. We also look at things like shared proving to save costs, shared network effects, so using the layer 1 for network effects instead of the layer 2s. And we kind of logically centralize our network effects for a better user and developer experience. And also, of course, shared assets. So we want the canonical ledger of last resort for every asset to be on layer 1. We want fungibility between these rollups. That's something that we get with shared deposits, but it's a big priority in of itself. Contract calls, of course. So we want to do contract calls. We want to batch those. Off-chain infra, that's pretty obvious. Security, that makes sense. And then, of course, economies of scale in everything we do. So one of these kind of tools is pre-confirmations. We have over here in number 1, we have a centralized sequencer that gives out pre-confirmations. This is what every layer 2 does today, except for Tycho. And number 2, we have some proposed models for based pre-confirmations, where the layer 1 proposer, the guy running on a Raspberry Pi with a dial-up, is the sequencer, and they're the one directly giving out pre-confirmations and directly interacting with the people who are requesting pre-confirmations. So obviously a pretty huge bandwidth and compute resources cost. And number 3 is the design being explored today, which is some form of delegation, that's that purple line, to a gateway who actually gives out pre-confirmations to users, and then they create some builder constraints, some set of rules that builders must build blocks that comply to, right? So the gateway is acting somewhat like a relay in this case, but with a little bit more constraint around the builders. So we still have an auction taking place, very similar to Mev-boost. And of course, the builder gives the block to our Ethereum proposer, who goes and gives that out to layer 1. Now, the other thing that we want to do is MEV retention, censorship resistance, being included here, and of course, doing this all with preconfs, which turns out to be a really difficult problem. But we have some excellent research from the Ethereum layer 1 about execution tickets. So we've kind of extended this to layer 2 on base rollups. We have these things They look very similar to execution tickets. We distribute these in an auction, and then you must burn a ticket to propose a layer 2 block, although we do some of the burning and kind of registration early in the epoch and off-chain optimistically so that there's not an expensive thing to do on-chain. And of course, with this, we can throw in some no delay forced inclusion. So every rollup today has a drift where you can make a deposit transaction on layer 1, and then you might wait a few layer 1 blocks before that's included in layer 2. In a base rollups case, you can pretty straightforwardly build no delay forced inclusion right into a base rollup, which gives you, excellent censorship resistance equivalent to that of Ethereum. Now, one other important thing about next generation base rollups is checkpointing. So whenever Tycho calls this proposing, by the way, but whenever we want to kind of put our sequence onto layer 1, we need to make a checkpoint here. And this is a little red flag on my diagrams, but what we're actually doing is making kind of a point of atomicity, right? A layer 1 EVM transaction is atomic. You can't revert part of it. And because of this, you can do cross-chain contract calls based on that atomicity. You can also checkpoint together. That's this bottom left diagram where we share lots of checkpoints in one, which saves a ton of costs. The other thing we can do, of course, is other things while we checkpoint. So we can use layer 1 liquidity during our checkpoint, make this available on layer 2s. We can also save the states of things on layer 1. We could change the state of a layer 1 contract to simulate layer 1 execution, but actually doing the execution on layer 2. Cool. So one important kind of piece of technology, and probably the most important for the base rollup teams to compete on and be the first to, is validity proving and fast validity proving and shared deposits. So there's a whole bunch of ZK teams working on this. Succinct and Risio are two examples. And the goal is to take fast validity proofs for a whole bunch of layer 2s, combine these, aggregate these into one fast ZK proof, and then put this onto Ethereum in a shared deposits bridge contract that has funds for lots and lots of rollups. Now this has security kind of concerns. You have to trust your ZK, so we probably want multi-proving, and it's also today really slow. So the biggest competitive advantage of base rollups in the future will be how fast is your proving. Cool, so this is kind of the magic of base sequencing that we've been working on at Spire to some extent, of course. And that is using a censorship resistance committee to sacrifice liveness for censorship resistance. You can read more about this in our light paper. And then forward base sequencing, which is using a sequence posted in a layer 1 slot to affect a future layer 1 sequence. This enables you to do based sequencing and traditional shared sequencing at the same time, which is obviously super powerful. So if anyone from Espresso is in the room, take a look at this. Cool, so after we've done all this, what do we get? Harmony. And more specifically, deconstructing economies of scale to enable parallel innovation while maintaining network effects. I've said this in all of my talks so far this week, and it's so important, right? We don't want economies of scale to introduce centralization risks, and we want to promote parallel innovation as much as possible. The other thing, one of our important goals for the user and developer side is a monolithic experience, right? Nothing monolithic in practice, but we want to have the ability for users and developers to feel like they're on one chain, just to get that clearly better user experience. And of course, doing all of this while establishing infinite expressivity, giving builders the direct ability to customize whatever they want about the rollup, including execution environments, gas fees, etc. Infinite gardens, break walls. Next generation base rollups actually solve problems. Stay based. Oh, here's a quote from Heraclitus Drake. Stay based for one man's liquidity is another man's liquidity. Thank you.
Okay, thank you a lot. So we have a few questions. So if you do play.
Cool. So first question, what can Tycho do to become a next generation based rollup? Well, first of all, upgrade their bridge contract so it can share proposals and deposits and ZK proofs with other rollups, and then add actually good pre-confirmations. Yeah, they have a lot to do.
Okay.
Cool. Yeah, second question. As someone new to the space, I find it hard to factor out the marketing. How does your approach compare to Espresso? Sounds similar, at least. That's a good question. So Espresso is building a shared sequencer, and they're building a form of what they call based espresso, which is not actually base sequencing. They just call it that. It's a marketing thing. And the goal of Espresso is to unify layer 2s. The goal of next generation based rollups is to unify Ethereum and layer 2s. So we're involving Ethereum in the equation. But to get there, you can do shared sequencing. You can even involve the layer 1 sequencer. But that doesn't mean anything unless you do this checkpointing, unless you do this atomic synchronous composability. So base espresso will not allow you to do cross-chain contract calls.
Okay, thank you. Do you have any other questions? We still have time. Okay.
Sorry, haven't figured out to log into that thing. So you mentioned that there is a no delay force inclusion. I'm kind of curious how that works with a chain reorg, where the chain state kind of change after, like if you force like a deposit, for example, and a chain state changes with a reorg.
Right. So this is something that every base rollup must do, which is reorg with Ethereum. So in the case of an Ethereum reorg, then your base rollup must always reorg. It doesn't have to change anything, but it will reorg. And this is something that is very hard to fix in protocol. So we need an Ethereum upgrade to reduce the risk of reorg or decrease time to finality. But there are a lot of outer protocol things we can do. So if you get lots of proposers opted in the look ahead, you can just ask them not to reorg, have them put up some collateral, and you'll be able to reduce the risk of reorgs. And you can also like paste over it on the user experience side. You can have a solver or somebody take a duration risk. The user never has to experience a reorg. And then Spire is also working on like an RPC that's custom kind of retrofit to deal with common reorgs. One thing I would add is that base rollups will reorg as much as Ethereum does now. So I don't know how much you use Ethereum, but if you do a lot of DeFi or trading, you still probably never experienced a reorg that has affected your life. So I wouldn't expect that it's a massive user experience problem. Yeah,
right.
We would have to reorg.
Okay, thanks. And then, sorry, just another question. I thought cross-chain contract calls was very interesting, but I still can't imagine how it works, like, you know, across, let's say, like a bunch of different chains that all operates at a different speed, right? So could you have maybe provide like some practical examples with like a bit more details?
Yeah, come talk to me afterwards because that's a longer discussion. So all base rollups have a batching time of 12 seconds and a block time of theoretically less, right? And this means that the kind of composability you do between them can only happen at batching time because that's the only time when you have atomicity and synchronicity, right? And so we can compose every 12 seconds. So we can do a cross-chain contract call every 12 seconds. And then within that kind of boundary, we can't do any composability that is enforced by cryptography, right? We could still do like intents or other kinds of interop.
Okay, thank you. Please give a round of applause to our speaker. Okay, I think next talk will start in 7 minutes. Okay, and we're gonna resume our talks on layer 2s. So our next speaker will talk about beyond recursive proving for Starknet. Please welcome Gidon Kamfer.
Hi, everyone. Let's see if you can hear me. Okay, so the goal of this presentation is to talk about everything beyond recursive proving, but I'm not going to assume you know everything about proving or recursive proving. So I'll just begin with the basics and you'll follow me, I assume. So let's talk about the basics of a validity rollup. What composes a validity rollup? You have transactions. Sequencers select these transactions, define their order, and I'll use the term sequencer also for execution of these transactions. So if you're confused by based rollups where they separate the sequencing from execution, here I'm going to combine them. And they build the blocks. Once we have a block, the way a validity rollup works is that it proves the validity of the execution of these blocks using a prover instance and sends this proof per block to verify our contract on Ethereum, on the underlying layer 1. And once that proof has been accepted, a state contract tracking the state of the rollup is updated with a new state. Together with the state update, we also add what we call state diff, and we may include also messaging between the layer 2, the validity rollup, and the underlying network. State diff, just to make sure you understand what I mean when I talk about state diff, is basically the update to the state of the rollup resulting from the executed block. Validity rollups do not need to transmit the actual transactions that they sequenced to the underlying layer. There is no such thing as fraud proofs or anything of that kind. We positively prove everything happening on a validity rollup. And as a result, we can send much less data to the underlying network in order to be able to reconstruct the full state of the layer 2. So a state diff is basically just the locations in the state that have changed and their values. So in this simple example, D has been changed into X. So the state diff of the transition from state 1 to state 2 is just a single element, change location 3 to value X. What does it mean to prove a block? So basically what we're doing is we're using the context of a proof in order to prove the statement that we have seen a valid execution from a given state A resulting in a new state B, and the resulting state diff between state A and state B is such and such. So the statement is the transactions were correctly sequenced and the input state results in the output state. What are we doing on layer 1 for the validity rollup? In this simple basic validity rollup, we need to verify a proof of a block, which can be costly in some cases. We need to publish the state diff, typically using blobs on Ethereum. And we need to update the state, which is typically some contract call of the state contract tracking the state of the rollup on layer 1. As long as the blocks are significantly large, this is fine. But if we want just to have a few transactions per block on layer 2 or quick finality, this can become quite costly. So the basic validity rollup is good if you have either very large blocks or you have a lot of traffic and then you can still have a short finality on layer 2. Or you have long finality, and then it becomes less costly, but it's less effective because you have long finality. Enter recursive proving. Recursive proving intends to reduce the overhead of verifying the proofs per block. So let's begin with what recursive proving really is. So on the left-hand side, you can see the generic concept of proving. So basically, you have some statement and you want to prove that given given an input or a witness, if you like, there is a correct execution of the statement resulting in a given output. And what the prover does, it basically proves that the statement was run correctly on the input and that the actual output is the given output. The proof does not necessarily need to divulge the input, as we call it zero-knowledge proofs. But if you like to include some of the input in the output, you can just copy that within the statement. So how do we use this context, this concept to create recursive proving? Basically, we replace the statement with a new statement that just says, I verified 2 proofs and found them to be correct. So proof 1 with output 1 and proof 2 with output 2. You use a statement that performs verification, which is just an algorithm, right? So there's no reason that you can't build such a statement. And the result is the 2 outputs, the original outputs, you just copy them from the input to the output. So when we prove this statement, exactly like on the left-hand side, the result is a proof and the outputs that we want to generate, which in this case are output 1 and output 2. What does this mean? We've basically combined 2 proofs with 2 outputs into 1 proof with 2 outputs. Now we can use this construct in order to combine various statements, possibly totally different statements from different sources. If you like, we can prove statements from multiple rollups even, into a single proof and a series of outputs coming from the original inputs, or from the original statements, I should say. So in this diagram, you can see 4 different statements. There's no relationship between them. Each of them has their own input, creates their own output. And using recursive proving twice in this example, we result with 1 proof and 4 outputs. So what does a validity rollup with recursive proving look like? Very, very similar to what we had before. So you have the transactions, the sequencers, define the sequence, execute the transactions, and create blocks, just like before. In this case, let's say they accumulate 4 blocks. Then we can use recursive proving in order to prove these 4 blocks with 1 proof, as opposed to 4 proofs in the previous example in the basic validity rollup. And this proof is sent to the same verifier contract on layer 1. Then, for every block, a state update takes place on layer 1, on the smart contract that tracks the state of the rollup, and the state diffs per block are sent to layer 1. So using recursive proving, we've basically reduced the cost of verifying proofs on layer 1, but we still keep the concept of publishing state diffs per block and state updates per transition. So from state I to state I plus 1 takes place per block. It's less costly than before because sometimes a significant cost is on the verification of the proof. State updates are less costly, but the smaller the blocks get, the more significant the cost of these state updates become. So this allows us to improve, to reduce block times on layer 2, on the rollup, or if you like, reduces the need to perform large batching on the blocks on layer 2, but still, we'd like to optimize this further. Which brings me to beyond recursive proving, which is the topic of my discussion. We want to build something which we call applicative recursion. So let's define applicative recursion roughly in the following way. Here you see again the same recursive proving tree that we had before. We have 4 input statements. We combine them together into a single proof with 4 outputs. With applicative recursion, the difference from regular recursive proving is that here we're going to assume that all the statements come from a single application, so they have some kind of common semantics. For instance, these are 4 proofs of blocks coming from the same rollup. Then what we do is we use the same the concept of proving, but now for basically squashing the outputs together into a single output. So in this case, we'll have a new statement, which basically says, this is in the red rectangle on the bottom, basically we verify the last proof, so we make sure that the outputs are valid by using verification of this proof, and we perform a statement that is a valid combination of the 4 outputs into a single output. So the result is a single proof with a single output this time. So let's see what this output could contain, okay? So for example, if we're interested in aggregating state diff, here is an example of 3 state transitions. So we're moving from state 1 to state 2 to state 3 and eventually to state 4. In each transition, we generate state diff. So in the first transition, you can see that position number 3 has changed from D into X. In the second transition, we're touching positions 5 and 6. And in the last transition, the third transition from state 3 to state 4, we're changing position 3 again and position 6 again. So the result is the state called S4 on the bottom of the slide. But if you look at the resulting state diff between S1 and S4, there are only 3 changes. So there's no reason to transmit 3 state diffs with 6 changes, as in this example. So one of the things that we can do in the squashing proof, this final step of applicative recursion, is joining the outputs together into a single, more concise output. Now in reality, for validity rollups, it happens quite a lot that the same positions in the state are changed multiple times, even within a block, and certainly between blocks, especially if there are many, many blocks or large blocks. So this kind of aggregation is very important to improve efficiency of state diffs transmitted to the blockchain. But also other things can be done, and I'll go into examples in a moment. So now, a validity rollup looks like this. You have the transactions. As you know, they're sequenced and executed, put into blocks. For every set of blocks, we create a recursive proof. Then we do the applicative recursion because all these proofs relate to the same application, the same rollup in this case. So we can do that. And this single proof with the aggregated output, a single output, is sent to the verifier on layer 1. So we pay for verification just like we paid for verification in the previous example using simple recursive proving. But now, instead of doing a state update per block, we can do a state update per recursive cycle, if you like, for multiple blocks together simultaneously. So what does this look like? So we have the recursive, applicative recursion. Per recursion, we verify a proof, and per recursion, we publish the aggregate state diff in 1 or more blobs, and update the state on the contract that tracks the state of the rollup with a single state update that updates the state to the final state we've reached after multiple blocks. And of course, we can include messaging as before. So the more blocks we have per recursion, the lower layer 1 cost will be. And this basically scales infinitely depending on the latency you require to layer 1. This is actually what we are doing currently on our rollup called StarkNet. What else can be done in this applicative squashing, or if you like, in applicative recursion? So the basic aggregation of state diffs, as I mentioned, is just a straightforward aggregation. But you can also do more sophisticated things. For instance, if you want to represent your state in a more efficient way, so utilize your blobs more efficiently, you can implement, for instance, a compression algorithm on this data. Just deflating the data into much smaller form, which allows you to include more blocks on your applicative recursion. Of course, eventually, when all the blobs fill up, you may reach a state where blob prices could go up, or you have more blobs than could fit in a single transaction and things like that. That is something you want to avoid, so that's a point where you want to cut off the applicative recursion, so it's not really infinite, as I mentioned before. In addition, as I mentioned, you can remove the need to do update states per block, and if you like, you can generalize this into a concept of segmenting a very large computation into multiple segments. So if you prove that you've executed a program from some state A to some state B, and then you've executed the same program or continuation of the program from state B to state C, etc., an applicative recursion or the squashing mechanism can ensure that you've actually proven the complete execution of this program from state A all the way through state C or Z or whatever. So this is the generalization of the concept of applicative recursion. And you may have more ideas here, and the more creative you get, the more interesting it gets. So basically, if you think about it, the whole concept of recursive proving, applicative proving, are a few examples of off-chain proving. So these are proofs that are never submitted to a verifier on layer 1. So basically, they're only submitted to a new statement that verifies them off-chain completely. And there are other examples that are useful in this context, and I'll talk about a few of these. So one example could be, for instance, for a privacy-preserving exchange, for example. So let's say you have an exchange on your rollup on the blockchain itself. Typically, exchanges that are on-chain, they expose the positions of their users. Some users are very sensitive to this information because it divulges trading strategies. So what you can do is basically have a user who knows their own position execute some order on their position while keeping the position encrypted on the rollup itself, or on the blockchain, if you like. So in this example, if I go over the diagram, you store encrypted positions on the blockchain. Every user is involved in the encryption of this position by using their own key. They can read the encrypted position, decrypt it, and then execute an order on their own position and encrypt the resulting position. Now, if they prove to a contract that executes trades that this would be the result of their encrypted position if, for instance, they get a little more ETH selling a little bit of Bitcoin, then a trading contract, or if you like, an exchange, can accept that proof without actually knowing the contents of the current position. So, of course, this does divulge some information because we are telling the exchange by how much we are selling and how much we are buying. But anyone looking at the position of a given user wouldn't be able to decipher the current strategy of this trader. So this is one example where proofs can be combined into a blockchain in order to create a more private environment by using client-side proving in this example. There are variants of this concept where we trust the exchange with our private information, and then all the positions can be encrypted and decrypted by the exchange as part of proving. But this is one interesting example that can also be implemented on rollups or blockchains, as long as you have a contract that can verify proofs. On Starknet, we have contracts verifying Stark proofs. We also have a contract verifying Groth16 proofs. So you have a choice of building your application on top of that on Starknet today. Another example is for scaling blockchains. And this will be my final slide, so for everyone pressed for time. This is a little bit more sophisticated, but the idea is, let's say I have a bottleneck in terms of the capacity of sequencing and execution of what's going on in the rollup. I want to outsource sequencing to someone else, if you like. Or I want to shard my layer, my validity rollup, so that different sequencers can run together in parallel, sequencing different parts of the rollup, or different contracts, if you like, some segregation of transactions. So in this context, what you see here is something that looks like two rollups, but they are actually the same rollup. So you have multiple sequencers, each executing part of the sequencing for the rollup, and proving this sequencing is correct using the validity concept, where the output of this proof is the state diff, or the changes to the state in the areas that they're responsible for. An underlying sequencer, which is the validity rollup sequencer, can verify these proofs, completely remaining on the rollup. These proofs don't need to be sent to Ethereum. And by verifying these proofs, this rollup sequencer can accept the state diffs coming from these various shards, or what we call ZK threads. And when we combine the state of all the threads, we result in a single state of a single rollup that can be, as in the previous story, transmitted to Ethereum with various kinds of proving, resulting in a unified rollup that has all the state computed by multiple sequencers. So here we utilize validity proofs in order to scale a rollup. That's it. I think I have 3 seconds left.
Thank you. We have now a few questions. Could you question? So I think the first question is how is aggregating state differs from multiple blocks, and is it better than increasing the block time itself?
Aggregating state is better than multiple blocks. Multiple blocks is better than having a single aggregate block. I'll put it that way. Why? Because what users really want is finality on layer 2, on the validity rollup itself. So response times go down, the smaller the block is. Of course, if we would wait for an hour to aggregate lots of transactions in a block, then we would have huge blocks and the basic validity rollup would work, but finality on layer 2 would be very slow. I also want to answer about proving cost. It's a good question because in the past people thought that proving, I remember back in 2017 or 2018, the number thrown at people was that proving a statement was something like 4 orders of magnitude less performant than actually executing that statement. At Starkware, I think our initial prover reached about 2 orders of magnitude, which is called the stone prover. And today we're talking about stew prover, where execution of the statement is almost the same as proving the statement. So the cost of proving has gone down very, very significantly. Well, it's not the same, of course. You still have an overhead. But to prove statements today costs very, very little. So all this recursive proving, for instance, is done within seconds, every recursive step. So you get a very quick finality even of the recursive proof, and of course that doesn't cost much.
Okay, we have still time. So what's the current transaction finality on Starknet, if you can?
Yes, currently on Starknet you get finality on layer 2 within 2 seconds.
2 seconds, wow.
And these 2 seconds will be preserved in a decentralized environment where actually block times will go down to 2 seconds, and we will continue to prove every block. So that's where we can go with this technology.
And maybe could this be used for cross-rollup communications through a shared prover?
Absolutely. In fact, in Starkware, I should say, today, we already have a shared prover. It's called Sharp, for shared proving. And we use it for many systems together. So we use it for public Starknet. We use it for private StarkX instances, which are layer 2 platforms for exchanges. We use it for app chains of Starknet. And all of these proofs are combined into single recursive proofs. Some of them are applicative recursion, some of them are regular recursion, and all of this is submitted in a single proof, attesting to a huge number of execution steps across multiple systems. So of course, this could also be used for messaging between different rollups.
Do we have any questions from the audience? No? Okay. Thank you very much for your presentation. Please applause. Okay, we're going to continue with our next talk. So let me announce our next speaker who will talk about base pre-confirmations with MR Mev-boost. So please welcome Lin Oshtani.
Okay, hello everyone. Today I'm going to talk about base pre-confirmation with Mr. Mev-boost. I'm Lin Oshtani from Nethermind Research. Okay, so most rollups, let's talk about most rollups today. So most rollups today build their blocks using centralized sequencer. So users send their transaction to centralized sequencers, the L2 transactions. The centralized sequencer will sequence the L2 transactions, eventually construct these L2 blocks, submit it to the L1 block building pipeline, and then the L1 block will include these L2 blocks. And centralized sequencers are nice. They can provide pre-confirmations. And pre-confirmations, what are pre-confirmations? Basically, users, for example, user submits their transaction C to the centralized sequencer. The centralized sequencer will return a pre-conf, which will say, I will promise to include your transaction C at the third position of the L2 block after transaction A and transaction B. And then some time passes, and then the centralized sequencer will actually submit this L2 block. But the thing here is this pre-conf will happen way ahead of time, before the L2 block is actually submitted to the L1. So it provides good UX. So centralized sequencers are nice. They can provide fast UX via preconfs, but however, they're centralized. So big question here is how do we decentralize? So one idea here is what if we remove this sequencer role entirely? And this brings us to based rollups. So based rollups, the idea is to use the L1 block building pipeline to sequence not only the L1 transactions, but also the L2 transactions. So the user submits their transactions not only L1, but also the L2, and then the L1 block building pipeline will sequence not only the L1, but also the L2 blocks. So let's expand this L1 block building pipeline part. So this is like what the L1 block building pipeline looks like right now. The user will submit their transaction, and then there are going to be builders who are going to collect these L1 transactions, and then they're going to construct blocks. And then there's going to be many builders, and then there are going to be many blocks, and then each are going to submit a bid to the proposer. The proposer is going to select the most profitable block and then propose it. So the idea of based rollups is that let's use this same pipeline that was used for the L1, which is used in blue here, also for the L2 transactions, which is using the red arrow here. And based rollups are great. They inherit the L1 censorship resistance and liveness, because there is no external entity other than and we only have the L1 actors that we already have right now. And it also enables L1 composability, because these L1 builders, they will have full sequencing rights over the L1 and the L2. So they can act basically as a shared sequencer between the L1 and the L2, providing composability guarantees. But there's a problem, which is base rollups are slow, because there is no pre-confirmations here. So to address this problem, there's base pre-confirmations. So base pre-confirmations, the idea is this. Let's let the L1 proposer opt in to provide pre-confirmation during their slot. So the user can directly send their L2 transactions to the L1 proposer. The L1 proposer can directly respond with a pre-confirmation. And then later on, the L1 block building pipeline runs, and then the proposer will ensure that these L2 blocks are included in the L1 blocks that they propose. So one observation here is that providing pre-confirmation requires sophistication. Because the proposer here, you have to have some API or some RPC endpoint to provide the pre-confirmations, and you also need to run the L2 full nodes to actually sequence these L2 blocks. So they would probably want to delegate, and they will want to delegate to what we call gateways. So the idea of gateways is this. The proposer can delegate their pre-conf duties to gateways ahead of their slot. So the proposer can say, hey, this is my gateway. Please send your pre-conf request not to me, but to this gateway. And the gateway will be responsible for responding with pre-confirmations. And then eventually the gateway will sequence L2 blocks, submit it to the proposer will include it in their L1 blocks. So gateways are nice, but they have some problems, which is, first, the inheritance of L1 censorship resistance and liveness is degraded. Because now you have this gateway entity that didn't exist in the L1 block building pipeline that is now sequencing the L2 transactions. And now L1 composability is also made more complicated because you no longer have an entity that's sequencing both L1 and the L2. Because the gateway is sequencing the L2, the builder is sequencing the L1. So the question here is, can we introduce base preconfirmation while retaining the good properties of base rollups? And here comes our proposal, which is called Mr. Mev-boost. So it's acronym for multi-round Mev-boost. And the idea is this. So let's split the slots into multiple subslots, aka rounds. And in each round, let's run a Mev-boost auction to pre-confirm a partial block. So this whole L1 block building pipeline that's sequencing both L1 and L2, let's just run this whole thing many times during the slot. So instead of running it once in the 12-second duration, run it every 3 seconds, for example. And this pipeline is nice because there is no additional entity added to the pipeline. So there is no gateway here. And as a result, we inherit the L1 censorship resistance and liveness much better because there's no additional choke point to the system, and also enables L1 composability because the L1 builder now is like sequencing both L1 and the L2, or they're like pre-confirming both L1 and the L2 at the same time. Okay, that it is. Thank you very much.
Yeah, thank you a lot. So just a quick reminder to the audience, you can ask questions by scanning the QR code. And do we have any questions from the audience? Yeah, I was wondering myself if you can explain, how long you've been working on this idea and if you published any papers already.
Yes, there's a ETH research post titled the same thing, like based pre-confirmations via multi-round Mev-boost. I think that was like 2 or 3 months ago.
2 or 3 months ago,
Yes.
so people can find it on
Yes,
internet?
yes.
Okay. Thank you very much. Let's one more time give a round of applause to our speaker. All right, we're going to continue with a serious topic in cyber economics. So let me introduce our next speaker, who will talk about node operators' perspective on pre-confirmation transaction pipeline. Please welcome our speaker, Michael Moser.
Hi, everybody. Let me just calibrate this. Yeah, so I'm Michael. I'm head of research at Chorus One. We are a node operator with just about 3 billion in stake. Some of you guys might know us from some of our research papers, actually. For example, we've designed MEV mitigation on DYDX v4, which is a system that's currently in production. We were also quite early to timing games. We started kind of experimenting with this type of thing early last year. And then we think it's always important to strike a balance between rational competition and ecosystem health. So we've published quite a bit about our approach, right? And we took a very transparent angle to that. And I think philosophically, this presentation is an extension of that. I just want to talk about pre-confirmations from a proposer perspective. And maybe a more spicy way of framing this presentation could have been, timing games in pre-confirmations. What do they look like? And then secondly, what could an early approach to pricing pre-confirmations look like, right? I think, first of all, it's important to note that it's very early days. I think there's just one public pricing model for pre-confirmations. And so what I'll describe here is more of a general approach rather than, a specific model, because this will be very parameter dependent. And, in the spirit of rational competition, we'll talk about what it is that we do, but we might not have all the parameters public, right, naturally. So here's the agenda. I'll quickly walk through the types of pre-confirmations. Then I'll talk about the pre-confirmations pipeline from a proposer POV. Game A is kind of like a timing game, right? What that would look like. And then game B is pricing and optimal inclusion. So let's dive in. I think there's a lot of jargon flying around. And I think it's important to just bring these things back to what they actually are. There are basically inclusion pre-confirmations, and then there are execution pre-confirmations. And I think the key difference between those, you can really boil it down to the 2 points I give at the top of the slide. An inclusion pre-confirmation is just a credible commitment that your transaction will be present in a future block. But it's not a commitment of the transaction actually executing, right? The transaction may fail. So what the validator does is it tells you, I commit to putting your transaction in there. But then again, if it touches contentious state, there's a chance that it will fail. An execution pre-confirmation, by contrast, actually commits to the transaction being 1, present, of course, and then 2, subset, executed in the block. Therefore, it should not fail. Okay, so what does this mean in practice? Implication 1, execution pre-confirmations can touch contentious state, right? They also require the block to be simulated, because otherwise you cannot commit to a transaction actually landing, right? You need to simulate the block out as a whole to understand whether this is a commitment that can be credibly given. And then conclusion 1 from that is execution pre-confirmations are best issued by builders. And I think there's 2 really simple reasons for that, right? If we just demystify it. Reason A is that builders have private flow. And as a proposer, you don't see that private flow, so you a priori do not have the option of simulating a blockout fully, simply because not all transactions are available to you. And then B, builders also have kind of sophisticated pricing, right? This is something that they do in terms of, it's part of their competitive edge. For a proposer, it's really more about running infrastructure really well. Okay, I see the light went out, but hopefully the rest of my talk will be enlightening, right? So maybe I'll do my best. Inclusion pre-confirmations on the reverse don't touch contentious state, because otherwise, it's not something that you could commit to without giving the execution pre-confirmation. Which means they're typically best issued by proposers, and the reason for that is just that the proposer is certain to propose, right? With a builder, builder A may win the auction, but builder B may also win the auction. With the proposer, you know for sure that the proposer is going to propose the next block, and therefore you do not have to probability gate it, right? If you get a pre-confirmation from a builder, you always have to expect that that builder might not win the block, or it must solicit downstream agreement from the proposer, but with the proposer there is no such uncertainty, right? The proposer is quite certain, unless something really terrible happens on the infra side of things, which is unlikely. Okay, so let's zoom in on the latter point. Let's zoom in on inclusion pre-confirmation transaction pipeline for a proposer. Yeah, I kind of sketched it out a little bit there. There's of course a lot of nuance here, but I think to understand the general concept, it's enough to understand the general transaction flow, and then I think we can dive deeper into more granular detail. The generalized proposer inclusion pre-confirmation transaction pipeline, you basically have a transaction originator. It would be, maybe it's a based rollup, maybe it's a user, and that transaction originator would send the transaction to some kind of transaction aggregator, right? You do not want transactions to be sent to the validator directly, because then what functionally happens is it can be, it opens up a DDoS attack vector, and that would very badly reflect, for example, on home stakers. It also generally wouldn't be the way that people are set up in Ethereum. Right? On Solana, proposers expect a certain amount of traffic. On Ethereum, that's really not the case. So there would need to be some kind of proxy in the middle. You can conceptualize a little bit like a relay. And this proxy can do two further tasks, right? Either it just takes the transactions and then forwards a set of transactions to the proposer for the proposer to choose, pick and choose, or it does pricing itself. And when it does pricing itself, frequently the lingo that's being used is we are talking about a gateway here. So really, that's kind of where the path diverges. Okay, either this type of proxy does pricing or it doesn't do pricing. And then for the proposer, if you want to optimize, you have to be opinionated about two things. First, you must source transactions optimally. This is basically how do you interface with the relay, gateway, proxy, whatever you want to call it, in an optimal way. And then B, there's another scenario, or this is like a subset of scenarios where you can engage in pricing. And then three, there's also maybe another game where you can strategically play inclusion and exclusion. And we've actually published about this, right? But this is more relevant for execution preconfs. So if you're interested in that, you can find it on ETH Research. It's by Umberto, who's a colleague of mine, and maybe I just want to mention here, this is a co-op with two other team members, Umberto and Benoit, right, who are very, very active on this type of more quantitative research. Okay, really, let's take it back, right? Either transactions will be sent to a proxy, or transaction pricing can be delegated to a third party. And then to kind of close the slide, I want to just structure out these two optimization axes. Optimal transaction sourcing, what that would mean in practice, there may be something like a timing game, but in actuality, we would argue that it's a reverse type timing game. And and then there's a sub-game where some transaction types you might want to strategically include or exclude, but I won't talk about this today. And then secondly, for pricing, yes, if there's no gateway design and the validator does pricing, then you need to have an in-house opinion on that, right? I think in general, it's important to say that all of these things always exist on a risk reverse axis. For example, even in normal PBS timing games, if you push them really far, what you do is you simply delay into a flat curve, and you're actually on a very bad point on the risk reverse axis, right? So I think it's important to always frame that in terms of expected returns. Okay, let's talk a little bit about optimally sourcing transactions. Yeah, so this is a busy slide. Therefore, I'll take it step by step. You see two kind of axes of graphs here. There's two graphs at the top, and then there's two graphs at the bottom. And I think the way to read this best is the two graphs at the top correspond to the first large point on the slide, and then the two graphs to the bottom correspond to the second large point on the slide. I will explain. I think the first thing to notice here, to set up kind of the timing game, is that gas use is dynamical, right? I mean, it varies a lot between blocks, but then it also varies a lot within blocks. And if you look at the graph there at the top right, that's basically, you know, the gas per transaction distribution, and it's of course extremely skewed. And then if you look at the gas usage versus position, which is on the top left here, you will notice that, you know, like the higher a transaction position is in the block, the more gas it consumes. Okay, so let's just keep that in mind. The earlier transaction is in the block, the more gas it tends to consume, with, you know, some edge cases around background specifically, and the gas per transaction is distributed in a manner which is super skewed. And then the second information we need to set up our case here is that PBS timing games capture value by soliciting the block very late, right? So you send a get header request really late. You give the builder a lot of time to gather transactions, to kind of combine them, right, for 6x arbitrage to come in. And this is what you see at the bottom here, right? This is the way it works in PBS. So the bottom left graph is the number of transactions and, you know, kind of when they come in. And I think here the point to take away is just the longer you wait, the more transactions are available, so the combinatorial space is higher. And then the second graph at the bottom, which is on the right, is, you know, like the longer you wait, the higher the ratio of the bit to the max bit is, right? So basically the way you would read this is simply the expected value of a block goes up over time. Okay. And now let's look at the game kind of that we can deduce from these two categories of information. So conclusion one here is PBS timing games benefit from expected transaction gas use going up over slot time, and PBS timing games also profit from winning over transactions with mainland in the next block, right? Now for pre-confirmations, I would expect this to be quite different. And the reason for that is because the premium that you're willing to pay for a pre-confirmation, it corresponds to the service level you are getting, right? And let's say you can land anywhere between, you know, like within a 12-second time frame. If you land at like 11 seconds, then you're getting a certain service level. But then if you land at 1 second to the next block, do you really need a pre-confirmation, right? So there's definitely some, like an effect here, where instead of the expected value going up over time, you know, it might go down over time, simply because the service level that you provide via pre-confirmation, this is earlier, this is better the earlier in the block, right? You're just doing more. And what this would mean to us is that we can say the pre-confirmation inclusion premium scales with the expected wait time, right? And what this would mean to us is, on the one hand, we would expect pre-confirmation value to cluster early. Okay? So if you look at the PBS graph here, we wouldn't expect it to look like that for pre-confirmations. In actuality, the highest expected value per transaction, that would happen a lot earlier. And then you really probably wouldn't want to wait super long. Instead, what you want to do is you want to wrap the pre-confirmation auction up, and you want to give the builder more optimization time. And then if you take it really practical, we think there's an optimal early end to the auction. That is, you know, there's a function of the transaction arrival and distribution and the price decay, right? And we have some very specific thoughts on this, but unfortunately there's no time, right? So we'll need to dive into the next game. And this is pricing and optimal inclusion. So previously I mentioned that either a gateway can price it, or, you know, potentially a validator can price it, right? If you ask me for a hypothesis, I would say it's probably more likely for the gateway to price it, because I think node operators on the whole, as I mentioned earlier, are more set up to run good infrastructure, right? Pricing is not something that typically comes up. But yeah, that being said, let's go ahead and sketch out that quick model, right? I think the first thing to consider here is, earlier I mentioned that the gas usage of a transaction, that varies depending on where the transaction is in the block, okay? And let's approach this heuristically and say there are kind of 3 tiers of transactions in the block, right? There's like tier 1, which is super early, which is top of block, which is typically your 6x arbitrage. There's tier 2, which is kind of, you know, like mid block, and then there's tier 3, which is anywhere else in the block, right? can say like mid block to bottom of block, and then okay, so we have this heuristic. Is it valid? Well, we ran the statistics on it, and we, you know, like this is a p-value which is pretty small. If I read that out now, that would take the end of my presentation time. So these tiers are not you know, the same in terms of transaction usage, right? Sorry, in terms of gas usage. So it's a heuristic which is kind of, you know, like if you rigorously look at it from a statistical POV, it's fair. And then one conclusion we can draw from that is that validators compete for tier 2 and tier 3 transactions, because tier 1 transactions, they are just super tied to being at the top of the block, right? The sec-stacks arbitrage, you know, like there's no real discretion about maybe including it at a later point of time. It has to happen at that point in time, because it is tied to a certain price delta between a centralized exchange and the DEX. Okay. That being said, again, takeaway 1, there can be, you know, we can separate out transactions in the block into 3 tiers in a statistically valid manner. Takeaway 2, tier 1 transactions here really aren't you know, as useful for our pricing model, because we are talking about inclusion pre-confirmations which don't really touch contentious state in this way. That being said, let's sketch out the model, right? So the first statement that we can make is, well, what do we need to build a model here, right? Can we even do that? Yeah, I think we can do it, right? Because inclusion pre-confirmations do not touch contentious state. You can build a model solely on public flow. Okay, so the model can be built. That's premise A. 2, how would the model look like if we dig in a little bit deeper? Well, okay, so we have a base fee component and we have a priority fee estimation. Let's look at kind of some of the attributes of these two, right? The base fee is easier to estimate because it's discrete, and then the priority fee is a lot harder to estimate because it is continuous, right? So just there's a much larger space. The base fee we can generally frame as the opportunity cost of pre-conferring transactions, right? Because if you do not pre-confer a transaction, you can always get a future transaction which you know as a minimum incurs the base fee, and then the priority fee can be seen as something that's more akin to like a premium, right? Which it is in actuality. Even in a spot market, the priority fee would basically correspond to a premium. Okay, so how can we sketch out a toy model? Well, first of all, we need a way to forecast the base fee, which is you know, like something that can be reasonably done, and then we finalize a distribution of the priority fee over tier 2 and tier 3 transactions, because again, tier 1 transactions not as relevant for inclusion pre-confirmations. And then what we think is a good first way of approaching it is you take the base fee baseline, and then you add a percentile of the priority fee distribution as the pre-confirmation premium to it. And actually which percentile you add to it, I think this is largely a function of, you know, it can kind of, you can see it as a confidence interval of how well you understand transaction pricing in the future slot, right? I think this is a good way. So a good way of approaching it. We hope to publish a little bit more on it. Okay, I think for both the last game with timing and for this, it's important to look at things empirically. For that reason, this is something that will mature over time. But in general, I think this is an approach that is valid, you know, for either a node operator, pre-confirmation protocol, or whoever else is interested in that. Yeah, so I think I'm ahead of time. Thanks for attending, and this is it.
Yeah, thank you a lot. We have 2 questions. I will give you a chance to choose which one you want to answer first.
Sure. So I'll answer the question with the 1 vote first. Besides based rollups and MEV searchers, who else might be using pre-confirmations? Okay, let's take the taxonomy that I mentioned earlier in the presentation. between inclusion and execution pre-confirmations. I think for inclusion pre-confirmations, like it's going to be two cases. One is based rollups, and then the second case would be UX, right? Okay, so you can look at that and you can say, well, you know, waiting 12 seconds, is that really so bad? But then if you frame it differently and you say, you know, speed that's comparable to Solana, then that actually sounds a lot better, right? So for inclusion, I think it's UX, let's say wallets and based rollups. And then for execution pre-confirmations, I think that's kind of where searchers start coming in, right? And not only like atomic searches, but then there's a point where it gets relevant for sextex arbitrage as well. Yeah.
Okay, thank you. We still have a bit time. If you have any questions, we have microphones available. Okay, thank you a lot. I think it was a very interesting talk. I also not operator myself, not just a home staker.
Okay,
Thank you.
great, thanks.
hello again. We're going to continue with our lightning sessions. So our next speaker will talk about search competition in block building. So please welcome our next speaker, Akaki Magishvili.
Hello everyone, welcome to the presentation. So today I will talk about searcher competition in block building. So this is the paper title, and it was co-authored with Christoph Schlegel and Danning Sui from Flashbots and Benny Sudakov from ETH Zurich. And I'm a researcher at Off-Chain Labs. So motivation was MEV, and we know that there are many forms of MEV extraction, and I'm listing only the most popular ones here. So there is this text arbitrage, background, sandwiches, and liquidation. And in each form, there are also many different specializations that you can take as a searcher. And here the main point is that there are many different types, so searchers are different in their specializations. So it creates some kind of heterogeneity among searchers. So we tried to model this with the tools of game theory, and for that we need to identify who are the players, and the main player is validator or a proposer that proposes the next block, and then there are these specialized arbitrageurs that in the Ethereum setting are called searchers. And in current market there are also builders that aggregate searchers and also public mempool transactions, but we are ignoring it for this simplified game, because for us the fundamental players are searchers and the proposer. Okay, we denote the set of searchers by S that we can identify by their addresses. Then searchers submit their bundles of transactions to include in the block, and typically now they send it to block builder, but in principle they could have sent it to a proposer. Then from these bundles, there are some, in these bundles, there are some conflicts, so you cannot build the block that is the union of all bundles. So you can build many different blocks. For a built block, searcher generates some value, and the validator or the proposer also generates a value. So these are the smallest building blocks of our game. So we are abstracting away from all particular mechanisms, how they interact, and that includes builders, and we only try to understand who will get how much among these players, depending on their bundles. So for this, we are using tools from cooperative game theory. And for that, we need to define a value of a coalition, and value of a coalition is the best block that the searchers in this coalition build. If there is no proposer in the coalition, then the value is 0. So proposer or validator can block any or veto any block. So you need to agree with the proposer, the searchers. And this already gives a coalitional transferable utility game. And in these games, the most natural solution we think is the core. And let me define what is core. It's very simple and intuitive. The core solution gives payoffs to all players so that no coalition of players prefer to deviate from the allocation and create their own block together. Because if they can, they will. And so we need to specify the payments to all searchers and the validator of the global game. So there are nice properties that core has. First of all, it's always non-empty. You always have one solution. In particular, you can give all the value to the validator. But of course, this would be very unfair to searchers. And there are other core solutions too, often, but not always. So for example, there are cores such that searchers capture all the value. And if we have additive value over the bundles, then we actually have nice characterization of the core. So to make it more interesting, we look at the stochastic setting, where we have a number of opportunities denoted by M and number of searchers denoted by N. And each searcher generates some value for each opportunity. So we have this matrix. And by P, we denote the probability that each searcher finds each opportunity. Okay? So then we have very nice simple result that as soon as probability is slightly high, so it's larger than this 2 log n divided by n, and there are not too many opportunities, so m is less than n, then with high probability the validator captures everything. And this can be in particular empirically checked in the data. So thank you for your attention. Happy to answer your questions.
Yeah, thank you very much. So I posted one question. I wonder if you know how many search providers are currently in Ethereum ecosystem.
So currently, today, I don't know, but it's in the order of hundreds.
Hundreds?
Yes.
Oh, okay. And we have one more question. How do you know that the core is non-empty? And this is usually requires strong assumptions.
So we know because if you give all the value to validator, it satisfies all these inequalities that core requires. So it's very easy to check. And strong assumption is that, what you may refer as strong assumption is that validator can block any or veto any coalition. So that has a veto power, and that's why core is non-empty. And in particular, we give exact example of a core.
Okay, thank you very much. Please give a round of applause to our speaker. Thank you. So we're gonna have, I think, break, and the next session will start at 1:50. Thank you.
Hello? Yes, much better. Hi, everyone. We are ready to start our afternoon session. Hope you've all enjoyed your lunch. It's the last day of Devcon. How are you feeling? Yes? Woo-woo. Oh, come on, you can do better. Do a little bit more. Come on, come on. How are you feeling? All right. I'll take it. I'll take it. Yes. Thank you so much. All right. So just a couple of housekeeping announcements before we proceed with the talk. Feel free to take pictures or videos if you would like to. Just make sure that the flash isn't on so that you don't distract our wonderful speaker. And there will be a QR code for the session so that you can ask questions during Meerkat. You're probably already familiar with it by now. It's the 4th day. But yeah, make sure that you scan the QR code, submit your questions there, and upvote those that you find interesting. At the end of the talk, we'll have a short Q&A session. And yeah, without further ado, let's move on to our first speaker. So our first speaker is Xiao, a co-founder of Perpetual Protocol. Xiao is going to be giving a talk called Building a Cross-Chain DEX with Chain Abstraction and Intents. And in this talk, Xiao will explore leveraging intents and chain abstraction to create a seamless cross-chain trading experience. Let's welcome to the stage, Xiao.
Hi, good afternoon. I'm Xiao, co-founder of NicoDex. I've been building different things in Ethereum since 2018. I guess most of my friends don't know what I was working on. The thing we're building are just too complicated to explain. But this time is different. We finally built something that even my parents know how to use. So today I'm going to share the experience of building a NicoDex, a product that hides blockchain complexities away and aim to make DeFi accessible to everyone. So problem. We all knew there are so many usability issues. Gas, seed phrase, bridge, tens of layer 2s. There are just so many things you need to figure out before doing a simple transaction. And most of us, I believe, are offering different solutions from different angles. So like better login, another wallet, or a faster chain. But even if we have some great solution for part of the problem, but if some other step are broken, then users still cannot get their jobs done. I think, for example, just like someone want to buy her first coin, let's assume they have a perfect wallet, and the onboarding experience is just perfect. But it's very likely that he was stuck when he need to pick one chain from like 100 different L2. Or let's say now he has a perfect wallet and also the best DEX. And now he wants to connect his wallet into her the best DEX, but she might be mobile, and she don't know why. Just wallet connect sometimes just not connected, and nor the best wallet or the best DEX can helping her. Or maybe she finally overcome all the problems. And now finally the last step, she's going to buy the coin she wants. But turns out it might be a phishing link. Then he's buying the coin that actually not the coin she thinks she's buying. And the worst scenario is she might lose everything. Just because of this simple mistake. After spending so much effort, the risk and reward seems asymmetric. I think there's no like 70% usable or 90% usable. In crypto, it either works or it doesn't. So I think we cannot make it usable by just offering some partial solutions. We need to have a holistic approach that addresses end-to-end user experience. And users should not need to learn like 10 different tools just for solving one problem. Users just want to deal with one product instead of like 10 different tools. So, and from the entire process, we shouldn't mention any technical terms. Those crypto jargon is irrelevant for the user, normal user who want to get things done. And when we are talking about chain abstraction, it's not about technology. It's all about user experience. We need to start with user experience and work backward to the technology. So it seems like a very humble and simple request. The ideal flow for a normal user should be just like, for example, like a biometric login, just like most of other apps, and then deposit some fund, and then you can start to trade. In second, seamlessly in one app. But that's not the fact. And after so many years, seems like there are not many products offering this kind of experience. Probably not even one. So our approach is to offer a unified product, combine several powerful components, and that only integrate some trusted app with a native, consistent user interface to offer a seamless user experience. But then it's unlike traditional wallet that will expose user to unlimited app, which could break your experience, or maybe could be unlimited potential attack vector. And it's also not like traditional DEX that you always need another wallet to connect. And I'll start to share how the onboarding experience first. Can I play the video? Thanks. Oh, great. Thanks. So users should use a crypto like a normal fintech app. So in this case, you just use the passkey and create a wallet. And by the way, there's a second passkey is for creating a session key, but it's out of the scope today. But anyway, now you have a self-custody wallet without managing the seed phrase. So behind the scene, after that process, we'll deploy smart contract wallet that of course conforms the 4337 standard. We're using a smart contract wallet called Kernel, built by ZeroDev, a wallet as a service company. So when we deploy this kernel contract, we also use this passkey account as the main signer. There is one unique feature or constraint of passkey is it's binding to a domain, which means you cannot use this passkey in another domain. So it's nearly impossible to be phishing. But also, there is another downside that what if the site is down? So it seems like a recovery mechanism is a topic that we cannot skip. But the challenge is, if users still need to create another wallet for the recovery, but then it's probably they still need to manage the seed phrase, then it's our failure. So we want to have a mechanism that even users don't need to access the private key, or they don't even need to manage that, as long as they have an address that can receive the fund, even if it's like a centralized exchange address, or someone they trust, that still works. So our idea is just, it's very simple. So while user has the access to the passkey, so he can enter the fallback address that he planned to receive the fund when something goes wrong. And then he used the social login to create another guardian address, and then ask the kernel to grant a special permission to this guardian, that this guardian can trigger some recovery event that led kernel to transfer all the fund to this fallback address. This is only possible because of this is a smart contract wallet, at least for today. And this kernel contract also implement another modular smart account standard, ERC7579, that can make this smart account be extended with compatible permission. So for example, like in our case, this permission would be like, you only allow Guardian to trigger, to ask kernel to call a function that is transferred, and the receiver must be fallback address. So now user has a reliable self-custody wallet even when the site is down, or even if she lost the passkey. So after the onboarding experience, we're going to talk about how we combine, leverage the intent-based cross-chain swap and some account abstraction to offer a seamless chain abstraction experience. So first, let's start with a scenario that Alice wants to buy some ARB with USDC. Let's say USDC is from Optimism. Could you help to play the video? Thank you. So Alice should only focus on what asset she's going to buy and don't need to care about chain. And pick the asset, buy, that's it. Don't need to worry about any other thing. No gas, no bridge. And you can see there are both Optimism and Arbitrum in one place. We should unify Ethereum, 100 of Ethereum layer 2 into, feels like a one chain. So how does it work? So we'll go through this cross-chain architecture step by step, but should be quick. The concept is quite simple. So first, in Optimism chain, Alice broadcasts, send a sign order and broadcasts this order to express her intent. So now Alice wants to buy a minimum amount of Arbitrum with USDC. And then relayer pick this order, and then relay this order, send a transaction to a smart contract. The smart contract will pull some USDC from Alice to this smart contract, but lock the fund as an escrow. It will repay the USDC later to relayer once the he ensures the relayer finished his job. So in the Arbitrum chain, this relayer, since you know the intent, the order, and then send the transaction to a smart contract, and then smart contract will transfer the Arbitrum to Alice. And from Alice's point of view, the cross-chain transaction is done, the trade is done. She already received the Arbitrum she needs, and she already paid the USDC. She doesn't care it's in a smart contract or another relayer. But for a relayer, she needs to wait the cross-chain. There must be some like cross-chain messaging under the hood, and she must wait the cross-chain messaging to let Optimism chain know, okay, now relayer in Arbitrum already done his job. So you can imagine this cross-chain messaging is not that fast, but from Alice's point of view, it's a lot faster because once her trade is done, she didn't touch anything about bridging. So once Optimism confirmed, okay, relayer did his job in Arbitrum, then smart contract will unlock the fund and just transfer the fund to relayer. So this is just an overview of this architecture, and now we're going to zoom in a little bit on this smart contract component. So actually, there are several layers. So first, Nicodex as a user-facing product has another contract that conforms another cross-chain intent-based cross-chain swap standard, ERC 7683. It could allow different systems to work together to share infrastructure like orders and filler that can make this system more efficient. Under the hood, this 7683 implementation interact with another settlement layer. In our case, we use a cross protocol. And a cross protocol also work with another UMA oracle, optimistic oracle, to do the cross-chain messaging. So as you can see, relay seems like taking a bit more risk, but user is still not risk-free. As many other smart contract users, so there must be some smart contract risks when using this kind of complex architecture. But I think it's our job, I mean, the one who built a user-facing product, we should be accountable to deal with this complexity, not user. For example, like if something goes wrong, like, okay, UMA Oracle has an unexpected result, which may make user lose her fund. But it's impossible to ask Alice, the user, to act as a distributor during the challenge period. if we really want to do this kind of like chain abstraction thing, I think it's not only about make things easier, but also about dealing with this risk and complexity. If we abstract this away, then it's our responsibility to help users to deal with it. So today, we've shared an approach that to offer integrated experience that make DeFi usable, just like a normal fintech app. And we show how we can eliminate seed phrase and wallet extension by adopting passkey and embedded wallet. And we also show how we can abstract gas away and design a fund recovery mechanism thanks to modular smart account. And we also show how we can let user to buy most of the asset in almost every EVM chain in one tap and feels like in one chain without knowing anything about multi-chain. And now user can use DeFi and use crypto in one app instead of like 10 different tools. And we crypto native often think users should do your own research. But I think the truth is no one wants to do research. And even it's about dealing with the money. Most of the normal user, they still need someone to trust, to be accountable. Even what we offer is a self-custody solution. I think self-custody shouldn't be an excuse for us that don't care about user experience. If we really want to onboard 1 billion users to crypto, I think user-facing product like us should have the encourage to manage the entire user journey, to own every step, to make sure our experience meet users' expectation. I'm Xiao from Nicodex. Everything I share is already living in production for like 2 months. And I really hope we can make DeFi and crypto accessible for everyone.
Thanks a lot, Xiao. Now we have a little bit of time for questions, and thanks a lot for submitting a few. I see only one of them is upvoted, so let's start with that one. And the question is, are there more security issues in using intense chain abstraction versus fully on-chain alternatives like Uniswap?
Our approach is actually not that much different compared to Uniswap, but I'm not sure what kind of fully on-chain alternative like Uniswap. Because if you want to trade like a cross-chain swap in Uniswap, we are using basically the same mechanism. Unless you're talking about like doing everything in one chain and then bridge yourself to another chain, then but I think that's something that's not comparable.
All right. So let's move on to the next one. I don't know whether that one is counts as promoting.
I'm not from across, don't ask me.
All right, the next one is, how can the solver prove that it made the correct work? And are there any ways the solver could take Alice's tokens and not do the swap, but steal them?
Sorry, where is the problem?
So it's this one.
Oh, okay, thank you. It's gone. Anyway, I don't remember the problem. It's a bit long, but I guess it's not able to do that. Actually, Relay has more risk than the trader. Because if you...
Here it is.
Thank you. Solver doesn't need to prove it made the correct work. It's the cross-chain messaging protocol need to prove the solver did the work. And solver just need to, there's not much power from the solver. Solver just need to wait and hope the cross-chain messaging doesn't steal his money.
All right. The next question is, what bridges are you using behind the scenes to fulfill the orders?
We're using a cross settlement, but I don't consider this as a bridge because we are not using their liquidity. But it depends on how you define the bridge. We're just using that for for doing the cross-chain settlement. That is a bit different compared to bridge. At least that's what I understand this.
All right. The next one is your solver network open to participate in? Who is actually solving the user intents? How do you ensure users get the fastest and most efficient path?
Okay, the easiest way is we make it permission. So we provide liquidity within a certain time period to make sure we can always deliver and under our control. But of course, once it's maybe after some time of period, then it's everyone can to take this order. And because we actually try to rely on like the solver network across, but seems like because we offer too many different kind of assets, so there are only a few major assets that some other fielder want to take.
All right, all right. The next question is, how do you manage liquidity providers? Is there a separate interface for them?
We're right now for spot trading, we're just using we're more like a UI layer, like we just use like act as an aggregator to use others' liquidity from like Uniswap or other places.
All right. Can a user approve spending amount from the wallet when using the wallet in another app, connecting via Wallet Connect, assuming Wallet Connect connection is possible?
Technically, yes, but now we don't think it's easier to understand for normal users. So at least in our product, it's not supported. But yeah, it's technically doable.
All right. What is the backend between passkey and kernel validator?
And as far as I remember, now it's in zero dev.
Yes, it is?
Yes,
okay,
it is.
cool. You just got a confirmation. Lovely. Why PWA over native app?
It's just easier for us to launch. We just launched for 2 months. We don't want to wait for like another month to wait for native app, but that's also doable in the roadmap.
Cool. And there are a couple more questions, but I'm afraid the time is up for the Q&A. Feel free to catch Xiao after this and ask all of your questions, and let's hear it up for Xiao. All right. So the next talk will start at 2:20. It will be a workshop, so stay tuned. Hello. All right. Let's get settled in for the last session at the stage. The closing ceremony is going to be right after this. Hope you're all excited. Our next speaker is Ankit Chiplunkar, co-founder and head of research at Frontier and One Balance. And it's going to be a workshop called Speedrunning Chain Abstraction EIPs, or ERCs and or EIPs. And so in this workshop, we'll look at different EIPs in the pipeline across the cake stack and how they relate to chain abstraction. So because it's a workshop, we're going to do the questions a little bit more interactively. So feel free to ignore the Meerkat QR code that you see. Just raise your hand when you have questions and I'll get to you with the mic and we'll do it this way. All right. Without further ado, welcome to the stage, Ankit Chiplunkar.
Hello. Am I audible? This is supposed to be like a 90-minute thing, but the idea is to speedrun it. The core objective of doing this workshop is basically just explaining the grand vision of what we mean when we say chain abstraction, and then digging deeper into more technicalities about what are the different EIPs or ERCs across the stack that would help you accelerate or give the chain abstraction vision to your end users. One way how I describe chain abstraction is if you are an app developer, then removing the word chain, bridge, and gas from the user journey altogether is the final end state of how I see chain abstraction. And so if you're an app developer and the user does not see those 3 words anymore, they just go to your app, click a button, and get the execution they want, is the eventual end state that we imagine. As the MC already told, I want this workshop to be more interactive. Feel free to just stop me, raise your hand. We can have questions. We can have like a Q&A session. There are a bunch of ERCs that have their own like historical context and more technical depth. I won't go into like a lot of historical context and technical depth, but the core idea is just to explain like what it tries to achieve, and we won't get too much into the nuances, but like how it takes you closer to the desired end state is the objective of the workshop. Okay, so a few things. This is like the outline. The first thing is I just want to talk about the blockchain cake, or how we think like what are the different actors or different layers in the blockchain ecosystem. Then like what are the ERCs that interact on the permission layer? What are the ERCs that basically are required between the DApp and the permission layer? So permission layer is more like the wallet. And so the DApp and the wallet layer, what are the ERCs that you need to basically communicate between these 2 entities? And then what are the ERCs that are needed to communicate between the permission layer and the solver layer, so like the mempool layer? And then what are the ERCs that you need to communicate between like the solver layer and the settlement layer? We'll get deeper into like what each of these terms mean, but this is just like the broader context. And so like the first section is just about explaining like what is the grand vision of what we are trying to do. This is something that I call the united block spaces of Ethereum. If you think about the last bull cycle, everything was amazing. Like you had the DeFi summer, you just went to an app, you clicked a button, you had the thing that you wanted, you went to Yam Finance, you clicked a button, you were able to deposit into these DeFi ecosystems, and everything was super smooth. The only thing was you were paying $100 for a transaction. And so after that, this roll-up centric roadmap, L2 centric roadmap sort of emerged, and it was a solution to this like block space is becoming costly problem, but it has created a fragmentation problem. And so the L2 centric roadmap has brought us many block spaces. Some block spaces are red in color, some block spaces are blue, but they all commit data to the Ethereum L1, but they don't feel like united. There's just too much fragmentation. If you just look at like the UX that you are giving to the user right now, you have 3 different types of Ethereum. If you open like your Coinbase wallet, you have 3 different types of Ethereum. It just causes a lot of friction to the user. Whenever you try to change your network, it just pops up and says, hey, do you want to switch your network? And then the user like has to go and then click another button. And even if you want to transfer funds from one chain to another, it's like you go to an aggregator and then you send those funds to some other location. You like have these different options where the user can choose between time and cost, and it's a very like buggy and frictiony experience for the end state, and this is why it does not feel like united block space. Like imagine if you're living in the United States and every state had its own version of US dollar, and you had to convert when you're moving to one state to another in its own version of US dollar, then it won't be as smooth a UX. Or when you were moving from one state to another and you had to basically get a visa stamp whenever you move from one state to another, it would not have been as united. And so this, like, if you solve these problems, then the Ethereum ecosystem, the whole EVM ecosystem will feel united again. And so that is, I think, the final vision of what chain abstraction is all about. A little bit detour to just explain what we mean by the blockchain cake. And so we imagine like blockchain has different layers, and there are different parties who are operating at different parts of the stack, but they own, all these parties fall in like 4 broad categories, and they have their own sort of trade-offs that they are trying to optimize for. The first is like the application layer or the DApp layer. These are things like Uniswap or Aave. A user goes there. This is like a UX interface in front of the UX, in front of the user, and then the user goes there, clicks a button, gets the thing that they want. The main thing that application layer does is basically generate call data for the user. So the user goes to the website, clicks a button, it generates the call data that needs to be, or generates some sort of instruction that needs to be executed, signed by the permission layer, and then executed on the blockchain. So the thing that application layer really tries to optimize for is finding the application that the user wants and then reducing as much friction as possible. Then there is a permission layer, which are things like wallets. And so there are multiple parties who are doing different things in the permission layer, but at the end of the day, what they're trying to do is convert this instruction that is coming from the application layer into some sort of signed instruction that the blockchain understands and is able to execute and change state. And so the application layer is constructing some instruction format, and then the permission layer is basically converting that into a language that blockchain understands. So it can be a transaction, it can be an intent, and then it gets executed on chain. And then the solver layer is basically all your mempools. So in V0, you had mempools, and then as the MEV problem evolved, you had like more sophistication that developed on the solver layer. But at the end of the day, it's all about the step between signing and finality. Everything that happens to your transaction between signing and finality is what the solver layer cares about. It cares about liquidity, it cares about sequencing, it cares about all the different types of auctions you have. There are maybe 100 different companies who are just operating on the solver layer, but this is like the core trade-off that the solver layer tries to optimize. And then finally, the settlement layer, these are your blockchains and oracles where things get finalized, and then that becomes your root of trust. Maybe just as a warm-up, as a show of hands, can people just raise your hands? Who is working on the application layer in the audience? Wow, quite a few people. I did not expect so many. There's this joke running. There's a running joke in crypto Twitter, which is no one is working on the apps. Everyone is working on the infra. And then there's the permission layer. Like who is working on the permission layer, like the wallets and policies and intents. A nice, good set of audience over there as well. Who's working on the solvers? Quite a few people. And then settlement layer, like chains, oracles. Nice. A little bit less settlement layer people. Maybe they don't like chain abstraction that much, but it's fine. Okay, so let's look at the core trade-offs that each of these layers are trying to optimize for, and basically what decisions these players in these layers of the cake make. You get like different properties of your application. And so the core trade-off that the permission layer is trying to decide on is between UX and user agency. And so like you have one set of users who just use like hardware wallets, who verify the transaction hash, that if the transaction hash that they're actually signing on the hardware wallet matches the thing that they see on MetaMask or some other wallet. And at the other end of the spectrum, you have people who just use Telegram bots and they just send their private keys to a backend server. And so, but Telegram bots still generate like 20-30% of the volume. And so there is this trade-off between what great UX you want to give to the end user versus how much agency the user wants for them. And this is like a trade-off that app developers or dApp developers or wallet developers actually have to care about, and they lie somewhere or the other on the spectrum. Another interesting thing that has sort of emerged is like if you guys have used these apps or dApps which use Google SSO, all the Google SSO verification or authentication that happens cannot happen on-chain. It happens in some off-chain compute system. And so what the app that is doing Google SSO is doing is it checks if the OAuth token that Google has given you actually corresponds to the private key that they store in some secure enclave or secure environment, and then sign it. And so even apps that are providing you Google SSO are making this UX versus agency trade-off, where users who actually ask for Google SSO are letting go their agency, letting go of their censorship-resistant properties for a much better UX. And so it was very interesting for me to see like the rise of these apps which like let go some parts of the decentralization or the censorship resistance aspect for this improved UX. And it's coming from like a user demand. The second thing the second layer, basically the solver layer, optimizes or trades off between finding the optimal route versus giving you like an execution guarantee. And so if you imagine a world where there are multiple chains, a user is holding balances in 3 different chains, and says, I want, like a user is holding $100 on 3 different chains and says, I want $100 at the end of the day on chain 4, find me the best route, pull the funds, give me the liquidity. There is this trade-off on the solver layer between like, what is the best price that you can give to the user versus can you actually execute the transaction or not? And so that's the trade-off that the solver layer sort of struggles with. And finally, on the settlement layer, there is this trade-off between fees and execution speed. So like if you are trying to move messages across 2 different chains, there are different ways in which you can pass messages. Like you can either rely on the L1, L2 bridge, which has like 7-day delay, but that is like the most secure way of transferring funds. Or you can trust like some other bridge provider which has a multi-sig and it will give you just things instantaneously. And so there is this trade-off over there. There are some properties that obviously we don't like, but there's a breadth of options available, and that's what the settlement layer sort of struggles between basically giving you a better execution speed versus like the cost of time or cost of doing that execution. Any questions till now? This was a little bit heavy or not heavy. Any questions till now? No? Either I'm very good at it or no one is listening. But okay. So this is what I imagine the expected end state to be from a perspective of a dApp. So if like you're a dApp developer, this is what the end state of chain abstraction I think looks like, which is a user comes to your front end, a user comes to your dApp. They don't see these 3 words anymore. They don't see the words gas, chain, and bridge anymore. It's just abstracted away from their experience. The dApp basically is deployed on some chain. It's deployed on some settlement environment, L1, L2, L3, whatever is their prefers, be it ZK, be it EVM, be it maybe even the new versions of VMs that are popping up. The dApp is deployed over there. The dApp requests either the wallet or the solver layer what is the effective balance of the user on this particular domain, on this particular environment. And then knowing that effective balance of the user on that environment can generate the call data that needs to be executed on the environment. And so all the process of basically pulling the funds from multiple domains into the target domain, into the target chain, is responsibility of everything downstream. So like the permission layer, the solver layer, the settlement layer. The dApp, the only thing that the dApp cares about is what is the effective balance of my user over here, and then what call data I should generate, or what intent or whatever is the format I should generate to basically execute this. And so like users can hold funds, like if you get back to this united block spaces of Ethereum vision, then users can hold funds on these multiple domains at the same time. Like they can hold $10 on mainnet, $50 on Optimism, $30 or $40 on Arbitrum, and then the wallet or the solver figures out how to pull everything over from all these 3 domains and executes the call data on base. Maybe the user wants to buy some meme coin on base. User just clicks a button, gets the execution, and that's what the dApp and the user cares about. Any questions on the vision? Any challenges? Things people don't like? I'm getting good at sales apparently. So, okay. So let's take a step back. Let's only look at. So in my opinion, you need ERCs at these different interface points between different layers, and those are the things that we should sort of standardize. There are some like ERCs that I think are interesting on the permission layer, which give interesting permissioning or interesting properties to the apps. And so we'll take a little bit detour. We'll just look at the permission layer ERCs and then go deeper. Okay, so first ERC is 4337. So when Ethereum launched many years ago, I don't remember. Maybe Dror knows, but when Ethereum launched, everyone had EOA wallets. So like And your wallet basically is responsible for doing three things. It is responsible for giving you some sort of an on-chain identity. So like your private key, when it is converted into some sort of a hash, gives you an on-chain identity. Your wallet is responsible for signing, which is basically verifying if the thing that you are saying you want to do is actually coming from you. So it does auth. And then your EOA wallet is also responsible for basically constructing this instruction set to the blockchain. Over time, people sort of figured out that this is very like restrictive, and this does not have the proper properties you want for a very good UX. The thing that was limiting, there are a bunch of things that were limiting with something like this. Like one thing is you cannot have modifiable authentication. And so like if you want to do something like a multisig, then you would need to deploy a new smart contract on chain, which has its own sort of authentication mechanisms. People also call them policies. So you can have more fine-grained policies, like this app can only withdraw these many funds, or I can only execute $1,000 worth of transactions in the next 24 hours, stuff like that. So all that is doable on chain. All those like checks and balances are doable on chain. And then another property that basically dApp developers wanted was batching of transactions together. Basically, like the Flashbots API just does this, like ensures batching of transactions, and so like you have a big entity just formed to enable that property to the transaction layer. And then also because you can do batching, you can do like gas sponsorship, so that you can give the user $100 in ETH, let them do the transaction, and then withdraw $100 of any other token in your solver. And so like these two properties is what people wanted from a modern account, which is granular authentication and ability to basically execute transaction on behalf of the user. So like gas abstraction is also what people call it. And so 4337 gives you that property. I won't get into like all the details of what are the different types of instructions you can pass or enable, but yeah, these are the two properties. One thing that I think is pretty nice is 4337 is gaining momentum and gaining adoption, and so it will be like the default way how people deploy smart contract accounts on chain. But for a cross-chain setting, how 4337 is also important is if you are on some target chain and you want to execute a transaction on behalf of the user, but the user does not have any funds on the target chain, this message.sender property is very important for every dApp. So basically the way dApp authenticates if a request is actually coming from the user, it is by verifying if message.sender is the user or not. But if the user does not have any funds on the target chain, like the user cannot execute the transaction. And so how 4337 helps is if your user has a 4337 account, or if your user has this batching property, which will be possible with 7702 whenever the 7702 hard fork comes as well, the solver can just fund the user with the money that they want on the target chain and execute the transaction on their behalf. The user does not have to basically, the user does not need to be responsible for executing the transaction itself. And so it has many other interesting properties as well, such as DOS resistance. So like you always have a mempool which is decentralized, where transactions, you can just leave transactions and they will eventually be executed on chain. But I think from a point of view of the chain abstraction vision, this message.sender property is a pretty interesting one. The second one, which is like, we are still in the permission layer, we are still in how, like what are the properties that you give to your account, basically. Over time, people sort of figured out that we cannot create new accounts with new properties every time we want to do something new. We wanted some way of basically installing programs into your account. So similar to how if you have like a phone or if you have your laptop, you install applications into these hardware devices, you can basically install modules into your account and get properties. Like another clean thing about this modular smart contract design is someone can just basically create one module, make it public, get it audited, and everyone in the ecosystem can basically just install it and get those properties. Any questions till now? No. So like the three main modules that are available. One is the validator module, where you can basically install, you can install these validator modules, and the only thing that the validator module does is basically checks things before an execution happens. The second thing is the execution module, which actually changes state on chain. And then there are pre and post hooks where you can do some conditioning before and after an execution module. There are two different versions of it, like one is gaining more momentum compared to other, but both try to solve the same problem, which is how do you create this communication layer between an account and installable functions. The second type of ERCs are on permissioning. So imagine you have your Google account and you are able to permission applications. So whenever you connect your Google account via SSO, let's talk only about Web 2 world. Like whenever you connect your Google account via SSO to another application, you are basically giving them permissions to do something with your Google account. Permissioning standards or permissioning ERCs are similar like that, where you can basically give permissions of your account to some other application. And so there are quite a few applications already that are live, which sort of give session keys to the application. So if anyone has used Hyperliquid, then the thing that they do is you go over there, they attach some session key, maybe I think in the browser context or in their backend. And so you just sign once when you log in. And after that, you don't sign anything. You just click a button, and the session key behind that, who is responsible for executing or generating call data and making sure everything is valid, executes or generates the call data and signs stuff for you. So there's no MetaMask pop-up. Like the only time there's a MetaMask pop-up is when you log in, and after that, there's a session key that gets attached to the dApp, and then everything happens either on the browser or on the backend. I'm not exactly sure. So there are these two ERCs that handle that. I don't know which one will gain momentum over time, but yeah, there's this. These are in flux. The good thing that these also touch upon this UX versus agency trade-off that I talked about earlier on the permissioning layer. So like, if you don't want the user to be troubled by like a new pop-up every time you want them to do something, you can add a session key to their account, and then it will be just like a click of a button. And you can generate multiple signatures or multiple transactions just because they have clicked something once. There is another one which I sort of like, which is Merkleized signatures. It is not a standard yet, but so imagine a world where, again, let's take the example where you have funds on 3 different chains and you want to get the funds on some target chain. The thing that you will have to do is basically sign 4 transactions, withdrawing funds from those 3 different chains and executing the call data on the 4th chain. If you have something like Merkleized transactions, then you just sign once, like your MetaMask just pops up once, and all those 4 transactions are in some sort of a hashed format, and you just sign once, and it's like a one-click signature experience. That signature is valid across all the 4 domains, but it will only be executed at the particular chain ID that it has instruction on. So you can really give the user this one-click experience without making 4 different pop-ups every time for every different domain. Okay, so that was all about permission layer ERCs. Let's look at like the interface between the dApp and the permission layer. Any questions till now? Yes. Yeah, it's not. I think it's on Biconomy docs. It's not. It's not. There's no ERC for it, but it's just something that I like, so that because like using that you can basically do one click, sign 4 different transactions, all those 4 different transactions are just valid on their particular domains. And so you carry that information on chain, but the execution only happens for that particular chain ID. So in the permission layer, like just to recap, on the permission layer context, we looked at 4 different types of ERCs that are in flux that will smoothen this UX versus agency trade-off. One is on 4337, it gives you this message.sender property so that the user does not need to have funds, the user does not need to execute the transaction on the target chain. The solver or some other third party or even the dApp can do it for them. The second is how do you modularize, how you add more properties to your account. And once you unlock that, you can add like session keys, you can add these Merkleized signature type things, and you don't even need to write any of these anymore. Like people have written these smart contracts and got them audited, and you just need to install them in your account if it follows the standard. Okay, let's look at how the dApp should communicate with the permission layer. So this is another thing which is in flux. There's no ERC for it yet, but one end state, if you want to have like the united block spaces of Ethereum, is you need like the transfer should the bridge should be as easy as a transfer. So right now, it's like a very, very buggy experience. I just showed you how like when a user is trying to move funds from one domain to another, they have 50 different options and they need to choose between speed and cost. But one thing that you can do, and it's still, I don't know the exact specifics where it will land, but at the end of the day, this is what an address will look like. So it will have your normal address hash and then some information of the chain. And then every chain would have to register some sort of an ENS domain. That domain will have all the metadata that you need, that the wallet would need to basically unfurl where I should send the funds. And that is how you would be basically like pasting the desired address of the user. The other thing that app needs to do is even just figure out what is the user address. In cases where you have smart contract accounts or different types of authentication mechanisms, it is not very easy to figure out what is the address of the user. And so this is one way in which the dApp can communicate to the wallet saying, hey, just give me the smart contract address. Sometimes even the user might have different addresses on different chain IDs. And this is one way to basically request what are the available addresses for the user on all different chain IDs, and then construct the call data according to that. Another interesting thing that is happening on between this dApp and permission layer is there are these session scoped EIPs or ERCs that are being formed, which is the dApp can maintain a session with the wallet and only request certain scoped properties. So it can maybe only request I can read your balances, it can only request I can execute some transaction, it can only request I can change some properties on certain chain IDs. And so similar to how you have whenever you basically authenticate whenever you log in via Google SSO or Facebook SSO, you define some scope properties that these apps can unlock. There are these four CAIPs is what people call like chain agnostic IPs that give these session properties. So you can either create a session, revoke a session, change a session, or even like if there is a session that is active, just get a session. Very similar to how like a dApp in the Web2 world will interact with your Google or Facebook backend servers. Another interesting ERC or EIP is this one called batched calls or batch transactions. So it creates, so suppose in a multi-chain world or a multi-chain world, what you would want is to execute something on the target chain. You might want 4 different things to happen one after the other. Either 4 different user operations, 4 different transactions. And this is the way how dApp can tell to the wallet that, hey, I want these 4 or 5 different transactions. Can you execute them in batch? And instead of just sending one particular transaction, waiting for execution and then sending the another one, you can just send a batch of transactions to your wallet. And if it is a smart contract wallet, the wallet can execute it in the same transaction. It will execute those user ops. Or even if it is you can even send instructions to execute multiple user ops or multiple transactions on different chains. And so this is how you do like batched transactions in between dApp and wallet. Another interesting property it has is this get capabilities feature. So a lot of the stuff that is driving these sort of some of these ERCs between the dApp and the permission layer is the idea that you should have smart wallets but dumb apps. So the app should only care about what call data I need to execute, what is the slick UX that the user wants, but the wallet should care about all the other intricacies of how I need to bring the amount or how do I need to bring the assets to the final destination. This one is a combination of the scope and the call that you want to execute. Another interesting one is, so right now dApps need to basically get a list, have a sense of what assets the user has, and then query them with their node provider. So like, okay, does the user have USDC? Does the user have this? Does the user have that? And then just query them. This basically gives the responsibility to the wallet. And so dApp can just basically query, okay, for this address, what are the assets? Can you just give me all the assets? Or can you give me these assets and these balances? And so all that job that the dApp was doing to basically fetch balances is offloaded to the wallet, and only the wallet is doing that job. I think this is because a lot of this work is repeated across both dApps and wallets, I think this is a pretty powerful ERC. Yeah? I'm not sure. I think only ERC20 for now. I can get back to you, but I think only ERC20 for now. Any other questions? No. Yes. Yes. Can you use the
mentioned that we already have an execute batch function, right? In the ERC 43337. Is it using EIP 5792 behind it?
So in 4337, you can execute user ops one after the other in the same transaction. 4337, so it gives your account that property that it can execute these things in the same transaction. 5792 is only about between the dApp and wallet saying, I want these things to happen. And then the wallet needs to figure out if it is a 4337 account, then it can do it in the same transaction. Or if it is an EOA account, then it needs to do it one after the other. And so.
And what about like cross chains? Like if I have, let's say for example, gas fee, I don't have a fund on a particular chain.
Yes.
But I want to do some transactions, then how do we have to separately communicate between different chains for this?
Even that is like the wallet's responsibility. The dApp just says, these are the things you need to execute, please execute them. There is also like a flag where you can specify if these things can happen in parallel or they need to happen sequentially. And so that is how you can do some of the cross-chain
Thank
stuff. The next set of ERCs are between the permission layer and the solver layer. So how does your wallet communicate to the mempool layer or the solver layer that please do this? So the wallet has converted the instruction that is coming from the dApp into some sort of signed message that the blockchain should understand. It can be like a intent, or it can be a user op, it can be a transaction, like an EOA transaction. But yeah, by this point, at the end of the permission layer, the wallet has signed something for you. One way I think the distinction between applications and wallets is applications generate the call data, or instruction, and then wallets are responsible to sign them and convert them into a language that the blockchain can understand. Yeah, so one thing which is sort of popping up is this intent framework. Let me just take a sip of water. Any questions in between? Cool. So when you are trying to communicate between two chains, you can either send tokens, transfer balances, or you can basically send information or send messages across. And if you look at the things that an account has, it either has balances, so things that are fungible, assets or things that are fungible, and then it has some sort of like authentication scopes that are attached to it, like a multi-sig address or a session key or some other property or a policy. And so when you are in a cross-chain world, when you are in a world where there are different domains, you need to sort of sync up the authentication scope all the time, but maybe send the balances at execution time. Do you have a question? No, okay. So this one is about moving assets across chain. One interesting property when you're trying to move assets across chain is because assets are fungible, you can basically pay a solver or pay a sophisticated third party to just move those assets instantaneously. And so this is why you have these solver or intent type of frameworks that have emerged, where you have a sophisticated third party who takes some money and gives you this speedy execution. But when you're trying to move messages around, you cannot have loss. It cannot be lossy. When you're trying to move messages around and you're trying to basically maybe vote yes in a governance vote, you cannot vote a maybe. It has to be a yes. And so when you're trying to move assets, there can be some loss associated with it if the users are happy with it. But when you're trying to move messages, it has to use the most secure pathway to move it around. And so this is just a standard to move assets around. And you can think of it as like a cross-chain limit order, saying I want to give these assets on the input side. Can you just give me this asset on the output side? And then it's the responsibility of the solver network to figure out which solver to use, what fees to charge, all the minute details. But this is how the wallet can communicate with the solver layer about can you move these assets for me and get me these assets at the target chain. There's another thing that we have been working on, which are resource locks. And so if you think about a cross-chain transaction, there are three things that happen in a cross-chain transaction. One is you need to send a message on the origin chain. Then the second step is someone on the origin chain or someone on the target chain is waiting for finality. So you send a message or send a transaction on the origin chain, either to a bridge contract, either to a solver network, and someone on the other side, on the target chain, is just waiting for finality or waiting for inclusion on this first message. And once they are happy that they will get the money, they can execute the transaction. And so this is like this three-step process, very synchronous, 1, 2, and 3, that happens, which causes this like long delay in moving things around. And this is also how like centralized exchanges work. Basically, you send money to their escrow, they wait for a certain number of blocks, and then they can debit you the money. This is what you need to do to basically guarantee equivocation protection between two databases. We are working on this thing called resource locks, where you can convert the synchronous process into asynchronous process. And so if you are able to tell to the solver layer by whatever means, you can attach this lock on an account level, you can attach this lock on a token level. If you are able to communicate to the solver layer that you will eventually get paid, don't worry about it, just pay the user right now, you can convert this three-step process into like a very quick, like instantaneous process for the user. And that's how you are able to move assets instantaneously across chains. It has like an initial bump of actually users depositing funds into a lock, but once this lock is enabled, you can get instantaneous execution. I can show you a demo of how this works. So the idea is that you should be able to move funds cross-chain faster than you can move the funds on the same chain even. And so that is the, hopefully this demo works. Whenever I really want to make it work, it does not work. But just to give you like a recap, this is like the wrapper contract where users, so similar to how you have wrapped ETH, you can have a wrapper version of the contract where users just deposit funds. And similar to how when you deposit into WETH, you can use it on all the different dApps like Uniswap or Aave. Something similar, when you deposit into this wrapper contract, you can instantaneously move these funds across any domain. So this is a wrapper contract, and this is my address on Arbitrum. Let's just move. So I have already wrapped some funds. Let's just move a small amount of money, and what will happen is it will pop up like a simple permit to signature message that I just need to sign, and as soon as I've signed, I have basically sending to the solver the transaction. So I moved money from mainnet to Arbitrum, and it took like 2.9 seconds. And if I just, if you look, the transaction on the mainnet is still pending, but the transaction on Arbitrum has already happened. I already got the money. And this is happening because you can do this like asynchronous communication between two chains, and you basically get this, if you unlock something like this, you basically get the speeds of Solana across the whole EVM block space. This is live, anyone can use it, just test it out. But you can, yeah. There's no ERC yet. There's no ERC yet. It's just.
So how did you do?
We did not, we are writing an ERC, but it's just like a quick demo. The contracts are public. It's like a wrapper contract, which just, so the main question is, can the user revoke this transaction or not? If the user can revoke this transaction, then the user has double spent and the solver has not received the money that they paid instantaneously. The way this works is when the user deposits into this account or into this token, they are voluntarily opting into a time-locked withdrawal. So they can withdraw these funds permissionlessly only after some time lock period. But
it's still pending, so it's not really
I think it is
time
finalized. It
locked.
should be finalized by now. Yeah, it's finalized now. So the solver has received the money.
But like when you say 2 seconds, that's even less than the source chain confirmation time?
Yes.
And who are the party? Like, can anyone do it permissionlessly, or do you have some?
So right now
assumption?
it's in a permission setting. Like Peter from Relay is sitting over there who's doing it. He was waiting for the money. He was waiting for the money, but he paid it up front. But eventually, like you can also encode it permissionlessly.
But you can. You just said you can cancel, right? Like because
you cannot cancel.
You cannot cancel.
You cannot cancel.
Even though it's pending.
Yes, because you have locked the funds with that account or with that token contract, and the only way you can cancel it is if you unwrap those funds.
And the relayer is account.
Sorry.
Who put the money?
The user. Locked? The user voluntarily put the money into.
Before this happened.
Yes.
So before user put some amount of ETH, then they put the bridge instruction.
So let me take a step back. So over here, if you think about what is happening, at transaction time, user is paying this cost of finality or inclusion. But with the resource lock, the user, because by the act of depositing, has already paid that cost initially.
When did the person do it?
So whenever the user deposits, we wait for a certain number of times to save ourselves for reorgs, and then we can say that there's no risk to the solver if the user will, like, you will eventually get the fund.
But what happened to the brand new user who just want to bridge something from A to 1? It sounds like you have to do some setup job
Yes,
to pre-allocate the one.
Yes, yes.
So that when people do next time, it's faster. But if it's a fast time experience,
It is not.
okay.
Yeah, yeah. So yeah, you need to top it up initially, and only then you get the speed. Otherwise, you don't get the speed bump. There's another question at the back.
Oh, I was going to say, can you talk a little bit about capital efficiency?
About okay.
And like the reality is, you've got to lock up the assets first. Are you planning to put it, the methods that you need into, say, wrapped ETH or something else, so that you don't have to hold, one balance ETH or staked ETH, that kind of thing?
Yeah, that's a good question. So there are different places where you can put the lock. You can have a lock in this, like, in a module. So we looked at some of the valid, like, ERCs where you can put a lock, where you can code different things in the module itself. So you can either put the lock on your account level, and so whenever you receive the funds are logged itself after some time, or you can put it on a token, and so whenever you wrap it, you basically log them. But yeah, there is this initial friction, and so if the user has not logged it, it will go through this path. If the user has logged it, it will go through this path. Yes. First there and then.
Thank you. So this sort of lock is similar to how Gnosis Pay works in a way, so
Yes.
that if I as a user want to move money out, I have to wait a certain time before. So it's a 2 times transaction. I say I want to do that, and then I can move money out?
Yeah. So there are other things that also, like, if you look at this, there's not something new. This has been tried before by different people. They've just not named it. But there was Gnosis Pay who was doing it. So you need to do something like this when you need to put a card on your on-chain balance, because Visa or MasterCard wants, like, instantaneous guarantee, but on-chain it might take some time, or it might also be reorged. And so you need to put some locks in your account level. So Gnosis has put some locks on the account level to enable their card feature. I'm sure any other wallet who has their own card needs to put something like this, because Visa and MasterCard won't wait for 12 seconds or some finality guarantees. There's also this thing by Coinbase called Magic Spend, where you have funds in your like Coinbase centralized exchange, and you want to execute them or use them on chain at transaction time. They have a lock as well. The lock is on their centralized database. So wherever is the source chain, you need to have some to get, like, the snappy 3 second. And it took 3 seconds because it's a demo. Like, our indexers are slow, but ideally you should just sign the message, and it should take the time of the target chain. The target chain block time is the only thing that should determine. Any questions? Yes.
Yeah. Do you provide the source code on GitHub so we can dig a little more in the one if example?
It's not. I will make it public, but the code is there in the code is open source, so you can just.
So the smart contract, but I assume on the UI there is a bit of wrapping and off-chain packing. So I would like to read into it as well.
Got it. There is.
Maybe you have plans to publish it on your GitHub.
There are some docs. At the end of the slides, I'll share the link to the docs. But you can go to docs.onebalance.io, I think, and you should find all the docs.
Which docs? Okay, thanks a lot. Docs onebalance.io. Got it. Thank you.
Yes. So these are the documents. So you can just.
How do you handle reorgs on the source or destination chain?
So because the funds are logged, even if there's a reorg, you can just replay the transaction, and the solver will get the funds.
Can it cause a double spend in any way?
I don't think so, because like whoever is providing, there is some like entity that is, at the end of the day, what you're trying to do is solve for double spending, because you want the user to get the money first and then give the money to the bridge or the solver. And so effectively, whatever this thing is doing is solving for double spending. And the way this solves for double spending is make sure, okay, this transaction goes first, then this transaction goes first, then this transaction. Another way to look at it is it's like a account level sequencer or a token level sequencer, which is just trying to sequence transactions one after the other so that there's no double spend.
Yes, but you execute transaction on one chain and then on another. A reorg might invalidate one of them.
So the reorg might invalidate. So suppose a user signs a message, like a 712 message, send this much money to this address. First time transaction happens, then there's a reorg. Whoever is the paymaster can execute that transaction again and give the solver the money again. Because the funds are logged, because the resources are logged, the user cannot remove those funds. And so in the locking contract, you need to be sure that there is enough time that even if there's a reorg, the paymaster can replay the transaction. But yeah, so that is the only thing that you need to make sure. Otherwise, the solver will always get paid.
How much time is this locked?
I think in this demo it's 24 hours, but ideally it should be as long as you are sure that you can get the transaction included, even if there is some sort of censorship or reorg.
Thank you.
Yeah, more or less the same question. Sorry, I have to reiterate. So the input transaction, the user is supposed to submit the input transaction on the origin chain, right? But at the same time, you send it to the solver a signed raw transaction for the case that the input transaction on the origin chain gets reorged, so the solver can resubmit it anytime herself. But how do you deal with nonces, for example? You could invalidate the nonce with another transaction, and then it doesn't help that the funds are locked. You cannot use that signed transaction anymore.
That's a good question. So at least on the token level, since it's just using permit to, the nonce are not sequential, yeah. And even on the account abstraction level in 4337, you can have parallel nonces. So.
Got it. So you actually do not share the signed raw transaction. You share a signature, and the signature you can use in any transaction submitted by anyone, actually.
Yeah, a user op or permit to are just signed signatures. Anyone can bring them on chain.
Yeah, makes sense. Yeah.
And ideally, it's in the best interest for the solver to bring the source chain transaction on chain, because they've already paid on the target chain, and even if there's a gas spike, they'll try to get as much money as they can. So even if there's a gas price, they'll keep on like bumping up the gas and make sure that they get the money that they paid for. Any other questions? Yes.
Are solvers permissionless, so anyone can become? Or
Not yet.
Are solvers permissionless? Anyone can become a solver, or they've at least somehow?
In the demo, not yet, but ideally, yeah, you can have a permissionless solver.
Okay.
Okay, so this was how like the wallet communicates with the solver layer to get some properties. Either how you transfer value or how you get this instantaneous cross-chain UX. Now once the solver has done their stuff, how do you validate, or how do you actually validate if something has happened on the target chain? So suppose in the case of 7683, the user has just signed a message saying, I want this much money. The solver pays the money, but how do you make sure that the solver actually gets paid? Or if the solver does not pay the user on the target chain, how do you make sure that the user gets back their funds? This is what you sort of try to do in between these two layers of the cake. There are two standards. One is just like a message passing. So if you guys remember, I told you like there are two types of messages or two types of things that you need to move across chain. One is tokens or fungible assets. And if you're moving tokens, the user can basically take a price cut, take some loss, and get this faster speed. Or you are trying to pass messages across. And so this is one standard to move messages across, like bytes. And then there is another one to actually burn and mint tokens across chains. So there are two different standards. One is by Optimism Superchain. I think the 7802 is by Optimism Superchain. And then 7281 is by a bunch of different like bridge providers. It was called XERC20 before. But the core concept is that a token can assign a bridge to become a burn and mint bridge, basically. So when we look at the solver type of a transfer between chains, there can be some loss. But in a burn and mint bridge, there is sort of no loss. You can just it's as good as a transfer. It's effectively, yeah. Even if you look at the code, it looks like it looks very much like how the ERC20 transfer is executed. And the token basically trusts a burn and mint bridge, saying that okay, verify or validate that the burn has happened. Just mint me the equivalent amount of tokens on the target chain. So very costless way of moving assets. That's all I have for you guys. This is some shameless publicity for what we do, but we have two different products. One is like the chain abstraction toolkit. So if you're a dApp and you want to just get all these properties of you just need to care about what is the effective balance on the target chain, and this is the call data I want to execute. Just make sure it happens. Then this is the product that you would want. And then on the second side, we have another product that we are working on, which is the resource locks as a service. So if you want this, one token is just one representation of it, but then there'll be more modules that we build on top of it. And so yeah, that's the other product. Thanks a lot. Any questions? There's one question over there at the back, or no more? None. Oh, there is one.
Just asking if you could upload the slides, because there was a lot. I got almost everything, but not all of them.
So where should I send it? Sorry.
Twitter?
I'll post it on Twitter. If I am Ankit Chaplunkar on Twitter and Telegram, feel free to DM me if you need anything.
Thank you.
There's another question somewhere there, right? Or no? Maybe not. Also, I can see that a few people did submit questions through Meerkat. The one that got an upvote was how to support Sol and BTC.
I think effectively it's the same thing. You just don't have like ERCs there. At least the good thing about EVM ecosystem is you can have the same sort of language, but a lot of the stuff that we talked about will have to be changed a little bit for these ecosystems. But you can, at least from a resource lock perspective, you can put a lock over there as well, and you can instantaneously move. You can even instantaneously move Bitcoin from just at a click of a button to another chain. But there is like a lot of other stuff that you need. All the different ERCs that we talked about that need to be talked with these different ecosystems as well. And I don't know who is doing it. We are not doing it. I don't know if anyone else is doing it.
Another one is EIP 3370 already a standard for chain-specific addresses like base, 0x, ABC, blah, blah? What SafeX is using?
Yes, it is, but there's a different one. The main thing is like any chain can call itself base, and so how do you know what is the chain ID of the base? Any chain can have the same chain ID as well, and so with this chain specific address, like if you use ENS, then there is like a way to actually hoard that metadata on yourself, And the other thing with that proposed ERC is it will be permissionless, so a wallet can basically just run a light client and be able to get the metadata from that ANS ID.
Then we've got a question. How can a user ignore the chain? Aren't different chains with different security and performance properties?
There's a trade-off. Like some users won't ignore chains. Some users will be like, it happens right now as well. Like some users are like, I'll only hold Bitcoin. Some users are like, I'll only hold ETH. Some users want to trade meme coins. And this is just like a UX makeup on top of different properties that chains might have. Some users will care about it, some users won't care about it. And so if you are a dApp that wants to target the type of users that don't care about it, then use this. If you are a dApp that is very specific about, like the user should have all the context when they're trying to execute something like this, then the normal path is also available.
And the final question we have here is, how would wallets be deployed into different chains for initial setup?
There are different ways. So at least on deployment, I think one more interesting property that you get with 4337 is you get this deterministic address, and you don't need to deploy your account even when you're receiving funds on any chain. So you can just let the user receive the funds, and only when the user is trying to transact something that you can deploy the code of the account and then do the. So it has these nice like Sybil resistant properties as well. That is one way. There's another thing that if the user changes their multisig on one chain, how do you sync up? It's a different rabbit hole in itself. There's key store rollups, there are L1S load, there's a bunch of other things. We have not even touched about that over here, but yeah, that's a different rabbit hole altogether.
All right, that's all the questions we've got through Meerkat. Are there any final questions from the audience just spontaneously? Yes, can you wait for the mic so that everyone can hear you?
From the UX perspective, how long do you think it's going to take for us to be at a point where users and normies don't have to think about gas bridging and chains? Like, are we 2 years away, a year away, 5 years?
You can use these two apps. They are already in prod. There are a bunch of apps that are already in production. Users don't need to care about gas, chains, bridging, anything.
Okay. So
yeah, at the end of the slides, there are two apps that I link. They're just abstracted away. And if you're a dApp developer today who wants to get this like snappy UX, who wants to tap into all the different users who are on all the different domains, then you can use these things.
I guess the answer is the future is now.
Yeah.
Future, yeah.
Exciting
Future was
times.
yesterday.
Cool. Thank you.
Lovely. Anyone else? If not, let's give it up again for Ankit for this lovely workshop.
Thank you.
And that, my friends, concludes the program on the stage. Thank you so much for being here. Hope you enjoy the closing ceremony, enjoy Bangkok, enjoy your life. Thank you so much. Bye.